My name is Dan Ballou. I'm a web and mobile applications developer living in Madison, Wisconsin. Before we get moving, I wanted to tell you a little bit about myself. I built my first website at the age of 12 and really enjoyed the satisfaction of creating something from nothing. So I taught myself to program from books and videos online. I later became a freelance web developer and independent mobile developer. I currently work on a small team of developers creating training software. Last year, I founded CodeBallou.com, which is my personal blog where I post programming tips and tutorials. I'll also be using this website to provide you with additional resources throughout this course. In this video, I'll provide a high-level overview of what you can expect to learn in Mastering Swift 2 programming. In this course, we make sure to take a step-by-step approach as we uncover each crucial topic. And as we progress through this course, we'll build, analyze, and enhance one major application called Game of Life, and we'll also create a few smaller applications along the way as well. We begin with a Swift overview in Section 1, where we touch on many of the unique language features available to us. We also set the stage for several themes that are reoccurring throughout this course, such as functional programming and reference types versus value types. In Section 2, we look at Swift's advanced language features including extensions, generics, higher-order functions, sequences and generators, and more, all while building a classic programming application called Game of Life. We then move on to memory management in Section 3, where we'll learn how to analyze and optimize the performance of our application's memory. We'll learn how to isolate and fix memory issues such as leaks and zombies. In Section 4, we'll learn how to open our applications up to third-party libraries, whether they are written in Swift, Objective-C, C, or even C++. We'll also take a look at how to use the third-party dependency manager called CocoaPods. We then move on to Section 5, where we'll dive into concurrency and asynchronous programming. In this valuable section, we'll learn about threading with NSThread and concurrency with NSOperationQ, before turning our focus to the very powerful Grand Central Dispatch API. In Section 6, we'll take our debugging skills to the next level by learning how to use advanced breakpoints, LLDB commands, and the address sanitizer. We'll close this section by learning how to use assertions and error handling in our code. Section 7 focuses on maximizing the performance of our applications. In this section, we'll learn how to analyze and measure our applications for performance bottlenecks, and we'll see several ways to drastically improve the performance of our code. We'll also take some time to learn about how choosing the right algorithm for a given task can make a staggering difference in our application's performance. Finally, in Section 8, we turn our attention to design patterns. We'll learn how we can leverage the power of design patterns to solve common programming problems, while resulting in clean, readable code that is easy for future developers to work with. Once you've completed this course, you'll have a deep understanding of how to write clean, succinct, and powerfully performant code in Swift. You'll also know how to analyze and isolate performance issues, use Grand Central Dispatch for concurrency, interoperate with different programming languages, and how to implement design patterns. Before starting this course, just make sure that you're familiar with the Swift Programming Language Guide by Apple. If you're one of those programmers who won't settle for simply getting the job done, because you have a strong desire for a deeper understanding of how things work, then this is the course for you. In Mastering Swift 2, you'll be sure to learn how to write top-level code and get the job done. So let's get started. Hi, welcome to Section 1, Swift Primer and Intro to Functional Programming. The first half of this section will serve as a Swift review, where we'll be sure to highlight many of the important language features that make Swift unique. During the latter half of this section, we'll introduce functional programming, which will be a recurring theme throughout this course. Now, let's move on to the first video of this section, Swift Review, Operators, Types, and Strings, to begin our Swift overview. In this video, we'll touch on some of Swift's unique language features. We'll begin by discussing Swift's operators, types, and typecasting. We'll also be sure to spend some time discussing Swift's unique string type. One of the first things we notice in Swift is the heavy use of constants. We first define our stored properties as constants and only change them to variables when mutation is necessary. In fact, the compiler enforces this behavior with warning messages. Now, this is actually a good thing for our application's performance because it encourages us to use variables sparingly. Since constant values are guaranteed never to change, They are considered thread-safe and can be optimized by the compiler, making our code run faster. Swift offers all of the common operators that we'd come to expect in a modern programming language, including an enhanced version of the modulus or remainder operator, which, unlike many other languages, allows us to perform remainder calculations on floating point numbers. As with many other programming languages, performing calculations with very large numbers can cause overflow errors. Of course, Swift, being a safe language, offers a set of overflow operators that allow for extra safety when working with numbers that are either too large or too small. For example, if we assign an unsigned int 16 with a max value of 65,535 and attempt to increment the value using a simple operator, we'll get an error and our program will crash. However, if we attempt the same operation while utilizing Swift's overflow operator, we'll receive the value 0 rather than a runtime error. Swift also provides two useful range operators that are not found in the C language. Range values are shorthand for expressing a range of values. The first range operator ranges from A to less than B. The second ranges from A to B. We can use range operators like these with Swift's for-in loop to iterate over a given range. For example, we can write, for I in 1 through 5, print 3 multiplied by I results in I times 3. And we see our program iterates over each item in the range, much like a C-style for loop. If an operator we need doesn't exist, we can either overload an existing operator or create a new operator of our own to suit our needs. For more information and resources on Swift's operators, be sure to visit this video's resource page. Swift's basic types can be used just like their C counterpart types. However, in Swift, types are first-class objects, complete with their own initializers, functions, and properties. In addition to Swift's native types, we can always create our own types or import types from the Foundation library. Of course, we still have access to all of the Objective-C types, and many will automatically bridge from Swift to Objective-C's NS types for us. For example, if we take Swift string and assign it to NS string, the compiler automatically bridges from Swift to Objective-C's NS string. Casting from Swift to Objective-C, however, requires a typecast. Fortunately, Swift offers two useful typecasting operators to help us with this: the is and as operators. Type checking with the is operator is a way for us to check the type of an instance, while the as operator is a way for us to treat a given instance as a different subclass or superclass from somewhere else in its own class hierarchy. In functional programming, types can become very complex. Fortunately, Swift offers type aliases which allow us to create our own alias for any given type. Here we have a function with a type of takes two doubles and returns an int. We can simply assign this function type to a new alias and use it in place of our function's original type. This can come in pretty handy when working with very complex types. The string type is exceptionally noteworthy in Swift, granting a safe and efficient means of iterating and splicing strings with its native start index and end index properties. Swift even provides a subscript that takes an index to fetch a specific character. If you need to insert a string into another string, you can do so by utilizing .insert and passing it a string to insert along with an index to insert it at. Removing a range of characters from a string can be done by calling .removeRange and passing in a range. In fact, string is loaded with so many features that it actually meets all of the criteria necessary to conform to collection type, which would give us access to array-like functionality such as iterating through a string using a for-in loop. We could easily arrange this behavior by adding a simple extension method. This alone gives us the ability to iterate over a string with a for-in loop as shown. Having said that, a string is not a collection by design. Unlike strings, collections have a known beginning and end, which allows for random access, and iterating over them can be done reasonably fast. While on the surface, we may perceive a string to be made up of a simple sequence of characters, under the hood, each character is composed of Unicode scalars that might require multiple code points composed together. The reason I've decided to point this out is because it can be tempting to treat Swift string as a collection type to gain access to more methods of string traversal and manipulation, but doing so can come with drastic performance penalties and even bugs. We'll be discussing performance in depth in Section 7, Performance Optimization and Intro to Algorithms. In this video, we began reviewing some of the fundamental characteristics of Swift regarding operators and types. In the next video, we'll discuss Swift's collection types, arrays, sets, and dictionaries. In the previous video, we reviewed some of Swift's important operators and types. In this video, we're going to look at Swift's main collection types, which include arrays, dictionaries, and sets. The most common collection type is the array type. An array is simply a list of items of the same type. We're all familiar with the following array definition syntax, and we can define the same array in multiple ways. When using arrays, we get access to familiar operations that are available in other programming languages. For example, the isEmpty property is used to check whether the array is nil, and the count property is used to return the number of objects in the array. To access the first or last elements of an array, we can simply use the first and last properties, which will naturally return nil if the array is empty. We can also access an element in an array directly through subscripting, which of course can lead to runtime crashes if we fail to validate whether our index is within bounds. Since we have declared the array as a variable, we can easily append a value or a set of values using the append methods, append and append contents of. We can also insert a value at a given index using insert. This may all be common knowledge, but what's less obvious is that arrays in Swift have value semantics. In other words, their values are never shared. So when we create a new variable and assign an existing array to it, a copy is made. For example, in the following code snippet, A is never modified. This is because B is a copy of A, not a reference to A. Those coming from Objective-C are probably used to seeing arrays defined in two ways: NSArray for an immutable array, and NSMutable array for an array with values that can change. In Swift, we can define an immutable array by simply using the keyword let, rather than using var, which of course gives us a mutable array. For more examples and additional notes on arrays, you can visit this video's resource page here. A set is a collection type that will only allow the storage of unordered, distinct, hashable values of the same type. When the need arises to create a collection of unique items, a set is the best choice. We can define a set, much like an array, with var representing a mutable set and let representing an immutable set. In this example, we're looping through an array of 10 names and inserting each name into our set. Even though we're attempting to insert 10 items, our set only contains 8. This is because, unlike array, our set will not allow any duplicates. Set has many of the same methods and properties as array, including isEmpty, first, insert, remove, and more. It also comes with some useful comparison operators, including exclusive OR, which compares the left and right sets and only returns non-matching elements. Intersect does the opposite, giving us only the matching elements from both sets. Subtract returns all of the elements from the left, but with the elements from the right removed. Union combines the left and right sets, returning all of the items from both the left and the right. All of the operations we just looked at also have in-place versions which, providing we're working with mutable objects, function the same as the non-in-place versions, but rather than returning a brand new version of the set, they simply update the set to the left of the dot in place. Again, for more examples and resources on set, you can visit this video's resource page. The last of the common collection types that we'll be looking at are dictionaries. A dictionary is an associative array that stores keys of the same type and values of the same type in an unordered collection. With each key-value pair, the key acts as the identifier for its adjacent value. This key-value relationship structure makes dictionaries particularly efficient at storing and fetching values, which is most likely why we see dictionaries so widely used throughout the Cocoa framework for persistence. One such example is NSUserDefaults. We can define a dictionary like this. Notice that this dictionary is defined with a key of type integer and a value of type string. We can initialize the dictionary with values or assign values to it later via subscripting. Over here, notice that I've associated key 145 with John and 146 with Jane. If we want to access one of those values, we can easily do so through subscripting. We can also update values without the use of subscripting by using .updateValue. To remove a value, we can simply use .removeValue for key. There are also approaches to extracting values from entire dictionary datasets. For example, we can loop over a dictionary using a tuple, where the declaration on the left will represent the key with the variable on the right representing the value. We also have the option to extract a collection containing all of the keys or containing all of the values by using the .keys and .values properties. Obviously, I haven't covered everything here. If you'd like to learn more about collection type, I'll be maintaining some resources on this topic here. In this video, we've looked at some of Swift's collection types, arrays, dictionaries, and sets. In the next video, we'll review Swift's structs, classes, and enums. In the previous video, we reviewed Swift's collection types by discussing arrays, dictionaries, and sets. In this video, we're going to take a look at classes, structs, and enums, and open a dialog in regards to reference types and value types that will be ongoing throughout this course. Later in this video, we'll take a quick look at Swift's powerful enum type. In Swift, we can choose from 3 different options to store our structured data: structs, classes, and enums. If we look at Swift's standard library, we'll notice that roughly 90% of the public types are defined as structs, with classes and enums making up the rest. Not only does this demonstrate a preferred language convention, but it serves as a strong indicator of the importance of structs in Swift. It's important to note that classes are reference types, while both structs and enums are value types. Again, we'll be continuing this reference type and value type dialog throughout this course, but for now, we'll demonstrate how this works. We'll start by creating 2 variables, one for a first name and one for a last name. Next, we'll assign our first name with the value of John, and we'll initialize our last name variable to our first name variable's value. Of course, the value of John gets copied into our last name variable, which we can overwrite with a simple assignment operator. Now let's take this example a step further. If we declared a function that reassigns a given value accordingly, and then passed our value first name into our function, one might be inclined to expect our function to change the value of our first name's variable, though by default it doesn't. Instead, we're greeted with an error message. When we pass values into a function, a copy is made. This is exactly how we should think of structs. Of course, there are ways to change this default functionality. One way is by letting Xcode fix the problem by adding the keyword var to make the value mutable. Another way is by utilizing the in-out keyword, like so. Here we have the same example as before, applied to a struct named person. Person has 2 values in it, a first name, which is initialized to Steve, and a last name, which is initialized to Jobs. So our first variable, person1, contains the values Steve and Jobs. When I assign person1 as a value of person2, I'm doing the exact same thing I did in the previous example. So what person2 is going to point at is a shallow copy of the person object that person1 points at. So with our examples being similar, if we pass our person1 object into a function, again a copy is made. In other words, person1 still has the values of first name Steve and last name Jobs. Now let's see how a class handles this exact same scenario. We'll replace our struct with a class and instantiate our person1 and person2 objects, giving them both the value of first name Steve and last name Jobs. However, this time when we assign our person2 with a new first name, both person1 and person2 receive the new name of Jane. We'll notice the same thing when passing our person object into the same renaming function as before. This time, if we print out the value of person1.firstname, we'll get the value of Pat. So, thinking for a moment, what do we suppose the value of person2.firstname is? If we print out the value of person2, we'll see we get Pat. So that's the crucial difference between structs and classes. Hopefully, this begins to answer the question as to why the Swift standard library is composed largely of structs. Having said that, classes and structs are actually very similar, both having properties, functions, and initializers. So this begs the question, when should I use a class over a struct? We're going to do some performance measurements later in this course, which will make the answer apparent, but a good rule of thumb is, whenever our intended object has values that will change, use a class. Otherwise, use a struct. Before we move on, let's take a look at Swift's enum, which is another value type. Enums, in general programming, are structures that allow us to assign meaningful names to a set of integer values. Enums in Swift, however, are first-class types, much more flexible than in most other languages. Of course, we can use an enum in much the same way we do in C. In this example, the compiler assigns an implicit raw value to each case of 0, 1, 2, and 3. Though if we would have started north with a value of 250, for instance, our values would have incremented from that point like this. Enums are considered algebraic data types in Swift and can become fairly complex utilizing initializers, functions, and more. Let's take a look at one more enum example before we move on. In this example, we'll create a simple state machine called employee state, which represents 4 possible states for an employee to be in: clocked in, lunch out, lunch in, and clocked out. Then we have a method called next, which is a mutating method. This means that it modifies the value of the enum by assigning to self. Since enums are immutable, using the mutating keyword is actually the only way to modify its values. The way this method works is that it treats our enums like a states machine by moving our enums into the next state each time we call next. Let's test out our enum by declaring a variable and giving the initial value of employee state.clockedout. And finally, we'll call next to see our state machine in action. For further discussion on structs, classes, and enums, visit the resource page for this video. In this video, we looked at the differences between structs and classes. We also looked at Swift's unique enum type. In the next video, we'll review Swift's flow of control operators, patterns, and optionals. In the previous video, we began discussing reference and value types with classes, structs, and enums. In this video, we're going to take a look at Swift's flow of control features as well as optionals. By now, we're all familiar with Swift's for-in loops, which allow us to iterate over every element in an array without the possibility of indexing outside of the boundary of our array object. In this example, we iterate over a range by utilizing Swift's range operators. This syntax makes for an excellent replacement for the traditional C-style for loop. I should note that as of Swift 3, the traditional for loop will be deprecated in Swift. This for-in loop can easily be modified to iterate over a dictionary by replacing our single variable with a tuple of variables like so, and rather than iterating over a range, we'll change our data source to iterate over a dictionary. We can take this syntax a step further by adding a filter to our loop. Here, we'll iterate over a dictionary of words and return only the items whose keys are even. Swift 2 also introduced another for loop, the for case in loop, which we'll look at in the next video, What's New in Swift 2. As with many other languages, Swift also has a while loop, which, prior to Swift 2, utilized the familiar do-while syntax. Swift 2's version replaces the do keyword with a better-fitting repeat keyword. Do is now reserved for other purposes in Swift, which we'll look at in the next video. In this simple example, we're repeating the word hello while our count is less than 10. Of course, this is pretty straightforward and really doesn't need any further explanation. Now, switches, on the other hand, are exceptionally noteworthy in Swift because they have brilliant pattern matching capabilities. Here's an example of a simple switch statement which has a familiar syntax to many other languages. It's important to note, however, that in Swift, we don't need breaks. Breaking after each case is default in Swift, since a case does not automatically fall through to the case beneath it unless we explicitly tell it to. Rather than using a traditional fall-through approach, Swift allows us to use a comma-separated list, which allows for some interesting capabilities. For example, our current switch is not very exhaustive, so we can continue adding vowels after A to capture all of the possible vowels. Now, of course, we could leave this switch statement as is to capture every vowel, but what if we wanted to make a more specific list or even test for numbers? To show off some of Swift's pattern matching capabilities, we can add a case with a range from A to Z, and the compiler will recognize our pattern and allow us to filter characters. This is interesting, but we can take this a step further. We can change out our characters for ranges of alike words, case 1 ranging from the word any to the word apple, case 2 ranging from the word baby to buffalo, and case 3 ranging from Cayman to cousin. Our switch will automatically pattern match and sort incoming words into the proper case, like this. Swift switches can do more complex pattern matching as well. We'll pass a tuple into our switch that represents a latitude and longitude. Our first and second cases will match our variables as long as they're within a specific range. Of course, this is a simple example, and the numbers are loosely based on reality, but you get the idea of how powerful switches can be in Swift. To see more examples of what you can do with Swift switches, see this video's resource page. Let's finish up this video with a quick discussion on optionals. A very common pattern in programming is to have an operation that may or may not return a value. In some languages, like JavaScript for example, when coming across a null value, our program continues to operate just fine, as long as our program is not dependent on the value to continue. In other languages, like Java for example, a null value can create a null pointer exception and crash our program. Swift's solution to this problem is optionals. By default, if we define a variable without a value, the compiler will complain. So in order to declare a value that may or may not have a value at runtime, we need to add a question mark, which is known as wrapping our value in an optional. This is because we are indeed literally wrapping our value in Swift's optional type, thus giving it a value. To get a better picture as to what I mean by wrapping, we can look at how Swift's optional type is defined in the Swift standard library. If we print out a wrapped optional to the console, we'll see something like this, which is of no use to us. In order for us to use our value, we'll need to unwrap it. There's a few ways to do this. We'll cover the most common ways here. The first way is called force unwrapping and should only be used when we're positive that our variable will contain a value or when you actually want your program to crash if the value is nil. After all, there are times when your application simply cannot continue functioning without the expected value. In those situations, if we force unwrap a nil value, our program will immediately crash. In most cases, however, we'll want to unwrap our optionals in a much safer manner, like using an if-let statement, for instance. If-let allows us to attempt to create a new variable by extracting or unwrapping our optional value. If our optional has a value, our if-let assignment is successful and the value can be used. If the value is nil, our assignment fails, but at least we're able to provide a default value to stop our program from crashing. If-lets come with their own baggage, however, and aren't always the right choice for every circumstance. For example, unwrapping deeply nested optional values can result in a pyramid of doom situation, which looks like this. This happens because the if-let variable is only available within its own scope, causing each unwrapped value to nest in succession. Fortunately, Swift 2 resolves this pyramid of doom situation by introducing a new keyword called guard, which we'll cover in the next video. In this video, we looked at Swift's unique for-in loops and switches, and we also learned a bit about optionals. In the next video, we'll review the features added in Swift 2. In the previous video, we looked at flow of control, pattern matching, and optionals in Swift. In this video, we're going to take a look at the changes to the Swift language as introduced during Apple's WWDC 2015 conference. We'll take a look at changes to enum, option sets, pattern matching, guard, availability checking, and more. Swift 2 enhances enums with associated value types. Now cases we specify can have associated values of any type, rather than a simple integer value. This allows us to define a common set of related cases and useful values as part of one enumeration. Swift 2 also affords us the ability to write an either associative enum. This gives us the ability to assign any two types and let our enum handle our values depending on the type it's been given. Swift 2 also introduces recursive enumerations. A recursive enumeration is an enum that has an instance of the enum as an associated value for one or more of the enumeration cases. Prior to Swift 2, if we tried to create an enum value that recursively called itself, we'd wind up with an enum of infinite size and our program would crash. However, in Swift 2, you can simply label a recursive case as indirect and it works as you'd expect. Option sets are a lightweight and efficient way to represent a set of booleans. In this example, we're using a C-style syntax to OR our options together. In Swift 2, the syntax has been updated as a square bracketed encased, comma-delimited list of options. Defining an option set is simple. We just create a struct and make it conform to option set type. Now we can give it a raw value to hold our bits and define the elements that we want for our option set. In the previous video, we discussed optionals and how unwrapping multiple option bindings will lead us to a pyramid of doom situation. The problem is that, when successfully unwrapped, the unwrapped value is only available within the if-lets success block. Swift 1.2 tried to resolve this issue by introducing compound if statements. But this still wasn't the ideal solution. Swift 2 makes our lives easier by introducing guard. Guard does things differently than if-let. When an unwrap is successful, rather than enclose the unwrapped value, the value is released to the rest of the scope. In this example, we see a pyramid of doom situation with an if-let statement. If we replace our if-lets with guards, our code is dramatically cleaned up. That said, if a guard statement fails, you must exit your current scope by either using a return, a throw, or a break inside the else statement. Additionally, if you're using guard within a loop, you can use the continue keyword. In the previous video, we looked at several examples of pattern matching using a switch statement. But sometimes switches are a bit heavy-handed for smaller tasks. To accommodate these situations, Swift 2 introduces pattern matching for the other control flow statements in the language. So now, instead of using a switch to match on a single enum case, we can use something like this. For_in also received this capability. Now, we have the ability to loop through an array of enum values and pattern match directly within our for_in loops, like so. Swift 2 adds built-in support for checking API availability, which ensures that you don't accidentally expose an API that's incompatible with the current operating system. Here's what an availability check might look like. If an availability check fails, Swift will report an error at compile time. Extensions give us the ability to take any given type, say string for example, and extend its functionality in such a way that it feels like a native part of the language. Swift 2 also gives us the ability to extend entire types. For example, we could extend collection type in precisely the same way we did with our string. We'll be writing our own extensions in Section 2, Advanced Language Features. Prior to Swift 2, do was a reserved keyword that was used in conjunction with a while loop. The do keyword has been replaced with the keyword repeat for clarity. The do keyword hasn't gone away, however, it's just taken on a new meaning. In Swift 2, the do statement is used to introduce a new scope that can optionally contain one or more catch clauses, which themselves contain patterns that match against error conditions. To be clear, variables and constants that are declared within a do statement can only be accessed within that scope. Swift 2 moves away from the traditional Objective-C way of error handling, where if the call fails, the error variable receives a value. Instead, if the function can throw an error, Swift requires that we add the keyword try before the call. By default, functions in Swift trap errors, but if we want to propagate the errors out of the function, we can include the keyword throws. However, in most cases, we probably want to handle our errors by wrapping them in a do-catch scope like this. We're going to be discussing error handling in depth in Section 6, Troubleshooting and Advanced Debugging. Before moving on, I'd like to mention that, as of December 2015, Swift has gone open source. There are many upcoming changes that we already know about. If you'd like to see the proposed and accepted changes for Swift 3, visit this video's resource page, where I'll be maintaining a detailed list of upcoming changes. In this video, we discuss the new additions to the Swift programming language as introduced in WWDC 2015. In the next video, we'll introduce the concept of functional programming. In the previous video, we discussed the new additions to the Swift language as introduced in WWDC 2015. In this video, we'll introduce the concept of functional programming in Swift. We'll discuss its benefits and take a look at when we should proceed with a functional approach. We're all well acquainted with object-oriented programming. That's the paradigm that most programmers learn first and utilize in the workplace. And although many new programmers have heard of functional programming, most don't have any experience with it at all. My aim here is not to argue the merits of functional programming over object-oriented programming. Object-oriented programming is flexible, intuitive, and very widely used. OOP is an undeniable part of almost every programmer's life. In fact, we dedicate a final section of this course to object-oriented design patterns. So what is functional programming? Finding a consistent definition of functional programming is tough, but here's how I define it. Functional programming is a style of programming that replaces the concept of objects with a series of stateless, immutable operations. This allows us the flexibility to pass functions into functions and return functions from functions. So what are the benefits of functional programming? For most of us, the real benefit to adopting a functional style is that our programs can be broken down into smaller, simpler pieces that are both more reliable and easier to understand. When do we want to use functional programming? Functional languages are ideal for when you have a fixed set of things, and as our code evolves, we can easily extend our functionality by adding new operations on existing things. That said, we can always use functional programming concepts within OOP. I've got more to say about functional programming in general, but in the interest of brevity, I'll forego further digression here. If you're interested in reading more or finding links to additional resources on functional programming, you can visit this video's resource page. Let's dive into some functional code to see what we're talking about. The goal of this demonstration is to look at what a functional programming solution might look like. So having said that, we won't be going into great detail here. Don't worry if you don't understand everything now. We'll break these concepts down in the next section. Open up Xcode and create a new playground. Name it Functional and click Next, and then Create. I'll go ahead and paste in some starter code and explain what we're going to be building in this demo. In this hypothetical situation, we're managing a business account where we're receiving payments for an iOS application in the App Store. We have an array of dictionaries with deposits, and another one for business-related withdrawals. We also have a dictionary containing our business partners, along with the percentages we pay them for their contributions to our app. Our goal here is to use the data provided to figure out what our net income is after all of our expenses. We'll start by adding a function called findNetIncome. In order to calculate our new net income, we need to add up all of the withdrawals and deposits associated with our app. Since we'll need to calculate them separately, this is a good use case for a new function. Here, we've added a new function named appTransactions that takes an array of dictionaries and returns a double containing the sum of our transactions for the given transaction type. We'll add a property named gain, which we'll call our appTransactions function, and we'll pass in our deposits array. Then we'll create another constant named loss, which will also give the value of appTransaction, this time passing in our withdrawals array. Next, we'll create a constant named net that holds the difference from our loss subtracted from our gains. Now we have to address paying our partners. We'll modify our findNetIncome function to take a closure named payPartners. This closure takes a double and returns a double. We'll need a function to handle our closure. Here we've added a function named payPartners that calculates what percentage of our net gain that each partner is entitled to, combines them, and returns the sum. Let's add a return value to our findNetIncome function that returns the difference between our net value and the result of our partner's closure. All that's left now is to call our function and find our net income after expenses. Add a new constant named income and give it a value of findNetIncome. We'll add a trailing closure with a variable named total, and then we'll return our payPartners value. Finally, we'll print out our income value. Again, we went through this quickly to see some functional programming in action. Now, don't worry if this wasn't all familiar to you. This was just a review. We'll be breaking down functional concepts in the next section. However, if this exercise was completely alien to you, please head over to this video's resource page for some additional exercises on functions, which should help bring you up to speed. We'll be taking a more functional approach throughout this course, starting in the next section, where we'll build a classic programming exercise called Game of Life. In this video, we introduced the concept of functional programming and discussed some of its benefits. In the next video, we'll introduce protocol-oriented programming, which nicely complements the functional approach. Welcome to the final video of this section, where we'll be discussing protocol-oriented programming. In this video, we're going to take a look at what protocol-oriented programming is. We'll look at how to use protocols to extend a type, and we'll also demonstrate how to extend a protocol. In an earlier video, we demonstrated some of the important differences between structs and classes, namely how classes are reference types and structs are value types. So, we understand that structs are safer and oftentimes more performant than classes. However, we also discussed a major trade-off when using structs over classes. Unlike classes, structs can't use inheritance, which, of course, is troublesome for extensibility and code reuse. Having said that, we're faced with the challenge of maintaining immutability while having extensibility. Protocols are the answer. But this isn't a one-to-one solution. Protocols are, in many ways, better than traditional inheritance. With inheritance, you can wind up with bloated classes due to being required to implement functions or properties that you don't need to attain your desired functionality. With protocols, you just conform to the functionality that you need. This makes your code leaner and easier to read. At WWDC 2015, Apple, along with a major revision to the Swift language, defined Swift as a protocol-oriented language. This definition could only be made with the advent of certain new language features, specifically protocol extensions, which, as the name implies, gives us the ability to extend protocols. Of course, extensions have long been one of Swift's best features. They allow us to add behavior to existing classes, structs, and enums, including those in the Cocoa framework, giving our applications added functionality with a native feel. And as of Swift 2, we now have the ability to extend protocols. The following protocol has a function definition for a generic shuffle function. Let's go ahead and add it to Swift's array class, which gives array a new shuffle function. This works great, but what if we decided later that we wanted both dictionary and set to have the same functionality? Prior to Swift 2, the only way to do this is to repeat our implementation. As you can imagine, this kind of repeated logic is undesirable and tedious. Fortunately, Swift 2 allows us to extend entire types. For example, if we wanted to extend every class in collection type with our shuffle functionality, we could simply extend collection type itself, and all of the types that conform to collection type will then automatically receive our implementation. Of course, we may not want to extend all of collection type with our shuffle implementation. Fortunately, Apple added another useful component to protocol extensions: type constraints. For example, you may want to limit your extension's functionality to collection types that are comparable. This can be done by utilizing the where clause within your extension definition. In essence, protocol extensions allow us to enhance an entire set of types without tweaking individual subclasses, structs, or enumerations. One could write an entire course on protocols, and while we do utilize protocols later in this course, due to time constraints, we don't dive into as much detail as we'd like to. So having said that, I will be maintaining some useful resources on this video's resource page. In this video, we discuss protocols and extensions and how in combination they can change the way we think about programming entirely. In this section, we covered some of the major language features in Swift, while noting some of the more interesting points like Swift string type, the differences between structs and classes, pattern matching, and more. Finally, we introduced functional and protocol-oriented programming. In the next section, we'll take a more step-by-step approach as we begin our exploration of Swift's advanced language features, while building a functional version of the classic application, Game of Life. Welcome to Section 2, where we'll be discussing advanced language features and functional concepts. In the previous section, we reviewed some of the many great features in Swift. We also introduced the concept of functional programming, which we'll be exploring more in this section. In this section, we'll be constructing a classic programming tradition called Game of Life. As we progress through our build, we'll discuss closures, extensions, generics, higher-order functions, and finally, sequences and generators. Now, we move on to the first video of this section, introducing Game of Life. In this video, we're going to go over the application we'll be building by explaining the origins and the rules. We'll then begin laying out the necessary boilerplate code. At the end of this video, we'll be able to run our application. Although this course is not intended to be an iOS development course, I have found it best to convey new concepts both conceptually and in the context of a real-world application. So we'll be utilizing this Game of Life application as we cover each topic, but keep in mind that the focus is on the Swift language. The application is just a byproduct. Game of Life is a traditional programming exercise, which some would go as far as to call the advanced version of Hello World. It's a cellular automaton devised by British mathematician John Horton Conway in 1970. A cellular automaton consists of a regular grid of cells, each in one of a finite number of states, such as on and off. In our case, pre-birth, living, and dead. Game of Life has been rehashed many times and in various programming languages, including JavaScript, Ruby, Scala, C, C#, and the list goes on. Of course, we can find many different versions written in Swift. Most are written, however, using the object-oriented approach. We'll be using a functional approach with our game, inspired by Colin Eberhardt's rendition, which looks very similar to what one might find in both Scala and Haskell versions. You can find a link to Colin's version of the game in this video's resource page, or just visit scottlogic.com, where he maintains a fantastic blog. We'll begin by building a non-optimal performing version of Game of Life, and throughout this course, we'll measure and test our code's performance, replacing bits and pieces until we end up with a much more efficient version of the game. Although we will be using Game of Life for many of our exercises throughout this course, we'll also be working with many simple demo applications depending on whether the exercise fits into the Game of Life ecosystem or not. So here's how the game works. Every cell will interact with each of its 8 surrounding neighbors. These are the cells that are horizontally, vertically, or diagonally adjacent. At each evolution cycle, the following calculations will run. 1. Any living cell with fewer than 2 live neighbors dies. 2. Any living cell with 2 or 3 living neighbors lives on to the next cycle. 3. Any living cell with more than 3 living neighbors dies. And 4. Any dead cell with exactly 3 live neighbors becomes a live cell again. So, now that we know what we're building, let's get started with the boilerplate code. Now, much of the code we're going to be writing in this particular video is either off topic because it has to do with core animation, or is specific to iOS development, or it's something that we already touched on in section 1. So, having said that, we'll go through this setup phase rather quickly. But don't worry, the rest of this course will be step by step. Let's open up Xcode and create a new project. Select Single View Application, and then click Next. We'll choose Game of Life for this project name, and make sure that Swift is selected for the language and iPhone for the device. Finally, we'll make sure that Include Unit Test box is checked. We'll be utilizing unit tests to measure the performance of our code later in this course. Click Next and select a save destination. We'll begin by adding the necessary code files to our project. To add a new file, we can either control-click or right-click on the project's parent group and select New File. Alternatively, we can create a new file by clicking inside our project navigator and pressing Command-N. In the left pane, we'll select iOS and then Source. Then we'll choose Swift File and then select Next. We'll name this file State and click Create. Here, we'll create the possible states for our cell class, which we'll create next. Create an enum, name it State, and give it a type of int so we can associate raw integer values with our enum. Finally, we'll define 3 cases in line, giving the first case the value of 0. Remember, the compiler will infer the values for all subsequent cases. We'll also add a static function named randomState that will randomly select a state for us. This will come in handy while initializing cells. Next, we'll write our cell class. Press Command-N and create a new file. Select iOS Source and then choose Swift File and click Next. We'll go ahead and name this file Cell and click Create. We'll create a simple class definition for our cell and we'll add 3 properties: an x-coordinate, a y-coordinate, and a state. We'll also add an initializer, which I'll paste in now. So we see that our initializer takes 2 integers, which represents an x and y value. And then we utilize our randomState function we declared a moment ago to set a random state. This does it for our cell class. Let's add another file to represent our cell's life cycle. Press Command-N, select Swift File, and then click Next. We'll name our file Life and click Create. We'll start by adding a simple class definition for life, and we'll add 2 properties to it. Our first property we'll name Cell, which will hold an array of cell. And our next property we'll call Grid Size, which will define the size of our grid as an integer. We'll give it a value of 20 for a grid with 400 cells. Since we want to supply a grid of cells when our life class is instantiated, we'll need to add an initializer which will do some work for us. We'll define an initializer that takes no parameters and contains a nested loop that populates our grid. We're going to come back to this later. Next, let's create a new Cocoa class by pressing Command-N and choosing iOS, Source, CocoaTouch class, and then click Next. We'll name our file GameBoard and make it a subclass of UIView. This class will be responsible for drawing our game for us. We'll add a constant that'll hold an instance of our life class. We'll create a simple initializer that takes a life object as its parameter and assign it to our life variable. Let's uncomment drawRect since we'll be using it to draw our game. Next, we'll add our required initializer. For brevity, I'm going to go ahead and paste the drawing code in since core animation is not directly related to the subject at hand. So we've created a UI graphics getCurrentContext object, and a colorForCell function utilizes enum switching to set the color of each cell based on its state. We've added a frame for cell function that returns a CGRectMake with the dimensions for each cell. Finally, we loop through our cells and put our two methods to work. Finishing up with our initial setup, let's go to our main.storyboard and add a view. Search for View in the Object Library and scroll to the bottom to find View. We'll drag a view out onto our view controller, position it, and then, with the view selected, click the Resolve Auto Layout Issues button and select Add Missing Constraints. Next, we'll show the Assistant Editor and Control-drag a connection from the new view to its view controller, creating an outlet for your view. Name it Board View. We'll add another variable named Life at the top of the view controller, which will hold an instance of our Life class. And then we'll create a variable named GameBoard, which will be of type GameBoard. Now, add a simple required initializer to initialize our GameBoard. Next, we'll add some simple initialization to our ViewDidLoad. What we're doing here is setting our GameBoard's frame equal to our board view, and then we're specifying where the center of our GameBoard view is. Finally, we add our GameBoard to the board view, which displays our grid in our view controller. Build and run, and you should see an entire board of cells in random states. In this video, we introduced Game of Life and set up our initial code. In the next video, we'll begin by adding our game logic. Along the way, we'll introduce and discuss closure syntax and functional value types. In the previous video, we introduced Game of Life and began constructing our application. In this video, we're going to re-evaluate our Life class's initializer. Along the way, we'll discuss lazy variables, closure expressions, and function value types. We previously created a class named Life that used two nested loops inside of its initializer to initialize our grid. To keep our code clean and readable, we're going to extract our loop logic out of our initializer. As always, we have some options for doing this. We could call a function or a class function from our initializer, and for processes like these, those options would work great here. For this example, however, I'm going to use a lazy variable. Lazy variables are usually better suited for cases where you either don't want to spend the resources until the variable is called, or for when your data isn't ready until a few moments after your application loads. Having acknowledged the use cases for a lazy variable, and despite the fact that we could easily use a function here, I'm going to utilize a lazy var for this scenario simply because it'll lead to some interesting dialogue in a moment and again later in this course. First, we need to initialize our cells array to avoid property access errors. Then we'll initialize our cells property using a lazy variable, which we'll name assign cells to grid. Let's create our lazy var. I'll go ahead and paste it in now. This is a simple operation. We create an array of cell and use nested loops to iterate over each item on the x-axis. Then, for each item on the x-axis, we're populating every value on the y-axis, thus populating our grid with cells. Finally, we return the end value to our initializer. Although I don't consider lazy variables to be an advanced topic, there are some interesting things going on here, so it's worth taking a moment to discuss. As you've certainly noticed, our lazy variable doesn't contain a simple object type or a primitive type. It's holding a closure type that takes no values and returns an array of cell. Functions are types, just like ints, floats, arrays, and almost everything else in Swift. However, there's not just one simple function type. Instead, each function signature represents its own unique type. Consider the following example. Here our type is a function that takes two int parameters and returns an int as denoted with the following type signature. If a function has no parameter, its type is simply an empty set of parentheses or just void. Let's continue with this example by explicitly assigning this type to a variable. Since we have set our function type as our variable's type, we can safely set the value to that of our multiply method, giving our variable the ability to accept and return values. We can then use this method by calling our variable and passing in two values. This is not dissimilar to what we're doing with our lazy variable. Picture instead of using the function's name multiply, we just use a closure expression and our multiply functionality within. Both function exactly the same. So, looking back at our code, our lazy variable is actually a function type with a closure expression. Before we move on, you may be wondering what this weak self-in means at the top of our closure. We'll be discussing weak and unknown references in Section 3, Memory Management. But for now, just understand that we're telling the compiler to make a weak reference to self, which helps to avoid possible memory leaks. But with this, we have successfully removed our logic from our initializer. In this video, we explored closure syntax and identified a function value type. In the next video, we're going to take a look at one of the most useful features in Swift, extensions. In the previous video, we pulled some logic out of our initializer and into its own closure. As we did, we explored function value types. In this video, we're going to take a look at one of the most useful features in Swift, extensions. They offer us the ability to extend any class, enum, or protocol, even if the source code is not available to us. If you recall the rules for Game of Life, the next state a cell will move to rests heavily on the current states of its neighboring cells. So we need a way to identify the surrounding cells along with their states. I'll paste in a function and break it down line by line. This cellNeighbors function takes a cell and checks it against every cell on the board to find its 8 matching neighbors. At the top of our function, we create an empty array where we'll put our neighboring cell matches. We'll ultimately use this as our return object. Next, we loop through all of the items in our cell array, splitting each against our given cell's Xcode and Ycode, subtracting the difference, and saving the absolute value into 2 separate variables. Now, we could easily pass our 2 separate variables as a tuple into a switch statement, and in a real application, I just might do that. But this is a good opportunity to put Swift2's new if case statement to work. We define an if case much like a switch. In this instance, we'll check our 2 values as a tuple to see if we have a matching neighbor. Matches are represented by tuples with the value of 1, 1, 1, 0, or 0, 1. So using Swift's pattern matching capabilities, we can check a single if case for a tuple containing 2 separate range operators that range from 0 to 1. Of course, there's a problem with this. Our range operators are capable of matching a value of 0, 0, which is not what we want. Fortunately, Swift2 has given us the ability to filter many different operations, including this one. So we'll add a filter that guarantees we'll never get a match of 0, 0. Then we'll add an else statement that simply returns false for all other cases. This Boolean represents whether the given item and the current cell items are neighbors. If they are indeed neighbors, we'll append them to our neighbors array, which we'll ultimately use as our return value. This is a lot of work for one function, and it really misses the mark when it comes to functional programming. So we'll split this into 2 separate functions. For instance, this evaluation stage would work nicely as its own function. Let's create a new function named CellsAreNeighbors. Give it 2 parameters, one named side A of type cell, and the other named side B of type cell, and it returns a bool. Let's move our if case logic into this function and update our cases. Now, in our cellNeighbors function, let's replace our check variable's default value with a call to our new function since it returns a bool value. This is much better. We've simplified our function by breaking it into smaller pieces, but we can simplify it further. If you think about it, all our function is actually doing is filtering out which cells are neighbors. This may be a good use case for an extension method. Extensions allow us to open up existing classes and add new methods and computed properties to them, all while giving our newly added code a native feel. Let's open up a playground and add some functionality to Swift string type. It would be nice to be able to get the length of a string without having to use characters.count. We can add this functionality by declaring an extension to string with one computed property. We can then use our new string extension like any other native feature. We can also extend types like double just as easily. This extension extends the double type to immediately convert liquid measurements from a given unit to cups. It doesn't stop there. We can also extend both enums and protocols if the needs arise. You can find more examples and discussion on extensions by checking out this video's resource page. Let's create a utility file for a quick extension experiment by pressing Command-N and choosing iOS, Source, and then Swift file. Name your new file Utility and click Next. We're going to extend Swift's array type to handle our filtering dilemma. We'll define an extension by using the keyword extension followed by the type being extended. I'll paste in the functionality and break it down line by line. Here we are defining a new function on array called getNeighbors. GetNeighbors takes a function and returns an array of cell. The parameter predicate represents a function that will evaluate the given element and return a bool. Finally, our extension returns an array of neighboring cells. Back in our live class, we can replace our logic with one simple line. This certainly has a more functional feel, but I'm not convinced that extending array in this manner makes sense. We shouldn't add blanket functionality to a given type for one edge case. If we're going to extend an entire type, we should make sure that our extension of that type makes sense universally. In this video, we explored extensions and wrote a neat little extension of our own. In the next video, we'll explore generics and utilize them to re-implement our extension to be more flexible. In the previous video, we learned how we can use extensions to extend classes, types, and more. We implemented an extension that filters our cell objects that find the neighbors of a given cell. In this video, we'll explore generics and see them in action. And finally, we'll revise our extension method to support any type rather than just cell, which will make our extension more useful. Looking at the extension we just created, what if we wanted to use this type of filtering extension for more general purpose use cases? We could easily define this extension multiple times, one for each type we're interested in evaluating, but this solution doesn't scale well when you consider the dozens of possible types you'd need to write for. Fortunately, there's a solution for this problem. Rather than trying to write for every possible edge case, we can simply use generics. Our extension definitions here are similar. The first thing to notice is our type signature. In fact, the same code will work for any similar type. So what we really want here is a single generic function that works with any type that conforms to the same protocol. Consider a scenario in which you're asked to write a function that returns the maximum of two given integers. Given such simple requirements, we could easily implement a function that takes two integers and returns the greater of the two. But oftentimes, your requirements change, and you'll be asked to apply the same functionality to, say, a floating point number, for instance. Of course, adding a duplicate function is a simple option. But what happens when you get a third request and a fourth request for the same max value requirement? Obviously, we want to reduce repeated logic as much as possible, and when the only thing changing for these functions is the type, we should utilize generics. Generics are a way to specify that a function or a class takes any type as arguments and optionally returns the same type when finished. Instead of providing a specific type, we'll use a placeholder name to indicate types that should be identical but can be of any type. Such functions are called generic functions. I should point out that the general convention of placeholder names is to use single characters such as T, U, E, K, or V, but you can use any placeholder that suits your needs. If we look closely at all of our max functions, we can see that they all take two arguments and return one argument, and the logic within is exactly the same. So, if we remove our input and output types and provide a generic placeholder, we'll be creating a generic version of our function to handle all related cases. I say related cases because what if someone decides to pass in two objects that our comparison operator can't handle? We'll get an error. While there may be some cases where our generic function can manage most types, we'll most frequently need to provide some sort of a constraint. We can add a type constraint to our generic declarations to specify which types our generic function or class will allow. We do this by specifying a class from which a generic type must inherit, or the protocol it must adopt by specifying it after the generic placeholder separated by a colon. In the case of our max function, we'll force any type that we pass in to conform to the comparable protocol. This is a much safer generic function. This renders our previous versions of Max redundant and serves as an ideal replacement. We can also constrain the associated types of type parameters to conform to protocols. For example, the generic parameter clause sSequenceType, where sGeneratorElement conforms to equatable, specifies that S conforms to the sequenceType protocol and that the associated type sGeneratorElement conforms to the equatable type. This constraint ensures that each element in the sequence is equatable. Of course, generics aren't just limited to functions. Entire classes can be generic as well, as long as the class works with a consistent type. Arrays are a perfect example of this. You can store any type of object in an array as long as it's a consistent type. Creating our own generic class is simple. Let's look at this task class example. You can put any type inside of a task class, but, like array, all items contained in the task class must be of the same type. Now that we've been exposed to generics, let's apply this to our extension method. One thing to note is that when using generics with class extensions, you do not specify the type placeholder in the extension, although you can use a type placeholder within the body of the extension. If we replace our cell type with Swift's array generic definition of element, we'll be able to reuse this function throughout our application. I'll also change the name of this function to something more general purpose like custom filter. Our extension function makes much more sense as a generic and now can be used for many different tasks. For more examples of generics, check out this video's resource page. In this video, we introduced generics, provided a use case, and re-implemented our extension to support them. In the next video, we'll introduce higher order functions and introduce Swift's filter function. Welcome. In the previous video, we introduced generics and saw how to create functions that can take any type. In this video, we're going to discuss higher order functions, their use cases, and their value proposition. We'll introduce the first of the higher order functions that we'll be covering, which is filter. Finally, we'll add filter to our game of life. Our custom filter extension has quite a few use cases, but, as you may know, functionality like this has already been considered by the Swift team. In our previous exercise, we've essentially re-implemented Swift's filter function. While the functionality of filter is similar to Swift's, our filter is not a perfect copy. Swift's filter looks more like this. You see that it has the ability to throw exceptions and uses a while loop with a generator rather than a for loop like ours. Swift's filter is safer, while ours can be a bit faster. Filter is a higher order function that is common in many programming languages. Higher order functions are functions that accept another function as an argument and can also return functions. Although higher order functions can make for relatively terse code, there's also an underlying goal. And it isn't just to save some characters. The idea is to get to the point quicker, to make readable code while doing away with much of the ceremonial boilerplate code that can hinder clarity. One of the big selling points to higher order functions is when we chain multiple functions together, which we'll see later in this section. As a disclaimer, I should point out that there usually isn't a performance benefit to switching your looping logic for higher order functions. Keep in mind that higher order functions are just abstractions of commonplace programming solutions under the hood, so the performance will usually be on par with the logic you're replacing. We'll be sure to do some measurements between some higher order functions and their lower level counterparts in Section 7, Performance Optimization and Intro to Algorithms. Let's return to the definition of Swift's filter function to begin our deconstruction of higher order functions. This may look a bit daunting at first, but we can break it down piece by piece to understand it better. Adding @noEscape guarantees that the closure will not be used asynchronously, used at a later time, or stored. The type of the includeElement parameter is a closure that takes a generator element and returns a bool. We'll be taking a closer look at generators later in this section. For now, just know that a generator is something that can give you the next element in a sequence of elements. We see that filter has the ability to throw and rethrow exceptions, something we'll get into in Section 6, Troubleshooting, Advanced Debugging, and Error Handling. The return type of filter is also an array of the same type as the argument to its closure, generator element. What this means is that the resulting array will be an array of objects of the same type as the parameter array. The logic inside of Swift's filter should be somewhat familiar. One thing to notice is that Swift uses a contiguous array rather than a simple array. Contiguous arrays are much like array, except they can be faster in some cases. However, they lack the ability to bridge to Objective-C. Then we have another generator and a while loop that does close to what we've done in our custom filter implementation. So, in short, Swift's filter method takes a function which, given an element in the array, returns a bool indicating whether the element should be included in the resulting array. Let's make some progress in our application by putting Swift's filter to work. So we've got the functionality to determine the neighbors for our cells. Now we need to add a way to determine which one of our cell neighbors are living. We'll add another function to our class called livingNeighbors. We see that this function takes a cell and passes it to our cell's neighbor array. Recall that our cell's neighbor array returns an array of cell. Since we know that the return of this function is an array of cell, we can simply chain Swift's filter function to it, which will check each item in our array to see if it has a state equal to living. Of course, we can always simplify our closures by utilizing an implicitly named variable, which will reduce our filter statement to just one line. This is an excellent example of functional programming at work. Now that we have a way to determine the neighbors of a cell and whether a cell's neighbors are living or not, we can employ the rules of Game of Life. In our evolve method, let's utilize filter to find all of the living cells and all of the dead cells. These are simple operations that compare the cell's state to the state that we're filtering for. Next, we'll implement rules 1, 2, and 3 in one call. Here, our filter is looking for live cells with fewer than 2 live neighbors and cells with more than 3 live neighbors, while filtering out cells that have 2 or 3 living neighbors, which, as the rules state, will live on to the next generation. And finally, we implement Rule 4. Any dead cell with exactly 3 live cells becomes a live cell again. Now that we've sorted out which of our cells live and which of our cells die, we need to update our states and display them on our game board. For now, let's just employ 2 simple loops. We'll loop over our new live cells and set their states to living. We'll loop over our dying cells and set their states to dead. Before we can run our game, we'll need to make some changes to our view controller. We'll need to add a way to set our game in motion. We'll do this by adding a tap gesture recognizer on our grid that will start a timer when tapped. At the bottom of our viewDidLoad, we'll define a variable named tap and assign a value of UI tap gesture recognizer with a target of self and an action of start timer. Then we'll add our gesture recognizer to our board view. Now, whenever our game board is tapped, our start timer function will fire. Let's continue by adding our start timer function to our view controller class. This function takes a UI gesture recognizer as an argument, though we won't be using it here. At the top of the view controller, create a variable named timer. We'll put this timer to use inside of our start timer function. We'll set our timer variable's value to nstimer.scheduleTimer with time interval. We'll set it to evolve every 5/100ths of a second, set its target to self, selector to moment, user info to nil, and set repeats to true. Next, let's add a method called initializeGame, which will randomize our cell states. This method will come in handy for when we want to start a new game. We see this method has a for-in loop that loops over each item in the life.cells array and utilizes our stateEnums mutating function to randomly select states. Let's open up our main.storyboard and add a button to our view, which we'll name Reset. We'll open up the Assistant Editor and drag an action from our new Reset button to our view controller. Make sure you select Action and name your new action Handle Reset Button Tapped. Then, inside the Reset Button action, we'll call timer.invalidate, which stops and invalidates our timer. Then we'll call initializeGame, which gives us a fresh game board, and then we'll call gameboard.setNeedsDisplay, which redraws our game board. Finally, let's create the method we specified in our NSTimer, named Moment. We'll call life.evolve and redraw our game board each time our NSTimer fires. Build and run, and you should see your cells come to life. In this video, we explored higher-order functions and discussed their value proposition. We also looked at and employed our first higher-order function. In the next video, we'll continue with our higher-order function dialog and discuss Swift's map function. Welcome. In this video, we're going to continue our discussion on higher-order functions by looking at map. We'll break down how map works and then we'll see it in action. We saw how filter reduced the amount of code we had to write by utilizing generics. In this exercise, we'll be replacing bits of logic with Swift's map function. The map function takes a closure as its single argument. The closure is then executed once for each item in the array, returning an alternative mapped value for that item. Looking at how map is implemented in Swift, we see the following. Like filter, map takes a generic type t. Next, we see the same no-escape decoration that we discussed with filter, along with a parameter named transform, which takes a function that has a generic signature. This function itself takes a type of generator element and returns a generic type of t. Map then returns an array of t, and just like with filter, we see that map has the ability to throw. Now, there's a lot going on in the body of map. For the sake of keeping these videos reasonable in length, I'm going to go ahead and send you to this video's resource page for a detailed breakdown of what's going on here. But for now, let's see map in action. We'll start by replacing some logic in our ViewController's initializeGame method. Here, we have a for-in loop that randomizes cell states on a grid. Let's replace this logic with our own simpler version of map. Open utility.swift and create a new extension on array. We'll name our function custom_map. It'll take a function which will transform our cell and then return an array of cell. Of course, this looks much like our filter implementation we wrote earlier. So converting our custom map into a generic map should be familiar. Let's start by exchanging each occurrence of the cell type with the word element. Finally, we'll adjust our for-in loop to handle generic types by removing any references to cell. This should work nicely. Let's utilize this back in our ViewController. We'll remove the original for-in loop and replace it with a call to our custom map function. This works great, and of course we can shorten this to one line if we wanted. The compiler can infer the type for us, and will even provide a default variable. We can swap out our custom map for Swift's version of map, and the compiler will be happy. Now, if we look at this code, we haven't really reduced the lines of code written, and we haven't made it any easier to read. This begs the question, was this exchange a good fit in the first place? In addition, why and when should we use map over a for-in loop? Let's take a moment to discuss when we should use map and when we should stick with for-in. Clearly, we don't want to replace all of our loops with map or with filter for that matter. We want to be deliberate when replacing code. In order to understand when to use map, we need to remind ourselves how it operates. Map takes our given closure expression and executes it once for each item in the array, returning a brand new array. While a for-in loop modifies, updates, or just simply accesses values in the original array. With that in mind, I'm going to provide some simple rules that you can choose to adopt if you want. Use map when you need to transform an array. For example, if we have an array of doubles and we want to convert each of them to a string that represents dollars, map is ideal. Use for-in loops when there will be side effects. For instance, when we need to change the value of a nested variable, write to a disk, or update the UI, use a for-in loop. Perhaps updating this bit of logic to use map rather than a for-in loop wasn't ideal. As a matter of fact, given these rules, changing our for-in loops to map becomes a bit more rare in general. This doesn't lend itself well for those aiming for a higher level of abstraction. Fortunately, the Swift team recognized this and introduced yet another higher-order function called for_each. For_each is a much better fit for our situation. Let's replace our map function with for_each. This seems much more appropriate for updating cell states, and if we compare this to our starting point, I think we can see an immediate benefit. Our code is readable and succinct. There are a few more places we can employ higher-order functions. Open your life.swift file and let's evaluate our evolve method. We've got two more for-in loops that we can switch out for for_each loops. And with that, our evolve method now leans entirely on higher order functions, while being succinct and readable. In this video, we looked at map. We also discussed when we should utilize it and when we should utilize for each. In the next video, we'll look at flat map and see what distinguishes it from map. In this video, we'll continue discussing higher order functions by looking at flat map. We'll see flat map in context by experimenting in a playground. Finally, we'll implement flat map in game of life. Flat map is useful while working with both single and multidimensional arrays, or arrays with optionals or nil values in them. Looking at the definition in Swift, we see that flat map takes any type that conforms to sequence type. Just as with map, the transform closure gets an element from a collection and runs the closure on each item in the array. Flat map then returns a type conforming to sequence type. As usual, I'll have some additional notes on flat map on this video's resource page. Let's look at a playground to see flat map in action. Here, we are defining a constant that consists of an array of arrays, also known as a multidimensional array. If we run flat map on our animals array, it will return a new flattened single-dimensional array. The flat map function also checks whether an optional value is non-nil. If it is, the value is passed on to the argument function. If the optional argument is nil, the value is excluded from the output array. Here we have an array of optional int values. Notice that we have multiple nil values in our numbers array, and our output array is not only flattened, but contains only non-nil values. If we perform the same operation with map, our function returns optionally wrapped integers along with the nils we passed in. Flat map becomes really interesting when we use it in combination with other higher order functions. Here we have defined an array of dictionaries that contain people objects. We're utilizing flat map to look at the flattened dictionaries and map to increment each value by 1. We'll look at more complex chaining in our next and final video on higher order functions. But now that we have a handle on flat map, let's use it in our game. In order to use flat map, we'll need some values to iterate over. We can change our grid size variable from an int to a range of int. I'll also shorten the name to grid. We'll comment out our for loop code for clarity. Next, we'll remove the value from our cells variable and reference our new range, followed by flat map. Then, in our closure, we'll add xin to define our closure's instance variable. Then, we'll repeat the same logic for our second loop, this time with map. In our map closure, we'll use yin for the instance variable. Finally, we'll create our instance of cell and then return our cell's variable. So far, this isn't any shorter, but we can work on that. I'll start by removing the yin and using an implicit variable. Then we can put map on a single line. This is much better. Actually, we can reduce this entire statement down to a single line by just returning our closures. If we're really going for shorthand, we can remove the self.grids and replace them with ranges like this. No more need for the weak self-in expression either. This is an excellent example of how much code you can reduce by utilizing higher order functions in Swift. In this video, we looked at how flat map is defined and how it works. In the next video, we'll conclude our discussion on higher order functions by discussing reduce. Welcome. In this video, we'll conclude our discussion on higher order functions by looking at and experimenting with reduce. We'll also look at how to chain higher order functions together to create really powerful and functional statements. Looking at Swift's declaration of reduce, we see that it takes two parameters. The first parameter, initial, takes an object of type t, while the second parameter, combine, takes a closure as an argument. The closure takes an object of type t and an element in the collection that reduce is called on. The closure returns the same type of object as the first parameter. As with other higher order functions, reduce has the ability to throw and rethrow. Finally, the return value for the reduce function is of the same type t. We get a pretty good idea of what reduce does just from its declaration. Essentially, reduce combines all of the elements in a collection into one single value. Let's open up a playground to see reduce in action. Here, we have defined a simple array of integers. Then we're calling reduce on our array and setting 0 as its accumulator. The closure is called on every element in the sequence and appends the element onto the accumulator. Then it returns the accumulator. This code, of course, can be shortened just like map. However, reduce can go one step further. Here, we are taking advantage of Swift's plus operator, which, being a function, can work on two separate sequences by adding the right sequence, in this case our transformed element, to the left sequence. Here's where higher-order functions become really handy. In a real-world situation, the items we're after are often encapsulated within another data type. In this situation, we can use map to isolate the numbers from the object, and then reduce to combine them. Here, we have a struct that represents an employee. It has two stored properties, a name and pay. Next, we have an array of employee objects. Let's say we want to define both the average pay and the total amount paid to all of the employees. First, we're utilizing map to isolate the pay properties for each of the employees. Now that we've got our pay objects, we utilize reduce to return the sum of the group's pay. Finally, we print out the average. For more examples and discussion on reduce, visit this video's resource page. In this video, we finished up our dialogue on higher-order functions by demonstrating how reduce can be used to accumulate sequenced values. We also looked at how function chaining can make our jobs easier. In the next and final video of this section, we'll look at generators and sequences. Hello and welcome to the final video of this section, where we'll cover sequences and generators. In this video, we'll discuss both sequence type and generator type and explore their definitions in the Swift standard library. Finally, we'll create our own sequence and generator type objects. Throughout this section, we've heard the term generators and sequences, but only in passing. In this video, we'll cover all of the necessary pieces to create our own sequence type. Let's look at the sequence type protocol in Swift. I'll open up Xcode and type sequence type in any Swift file. As you're probably aware, we can right-click and jump to the definition of the type. This is the definition for Swift sequence type. At the top of the comments, we see that the Swift team describes sequence type, a type that can be iterated with a for-in loop. As we scroll down, we begin to see some familiar code. There's map, filter, for each. These functions become available to us for free when we create our own sequence type. This is great, but what we're interested in right now is this portion of the definition. These are the pieces we'll need in order to create our own sequence type. We'll need a generator type, which is type aliased as generator. Then we'll need to return a custom generator with a specific element type when generate is called. Now let's take a look at the generator type. I'll right-click on generator type and click Jump to Definition. As we can see, this is a simple protocol containing just one mutating function, next, which returns the next element in the sequence. Let's start by creating our generator type. We'll create a new playground and define a class named binary number generator. And we'll make it adopt the generator type protocol. Next, we'll define a few variables. Final, which will designate our ending point, and count, which will increment and eventually reach the value of our final variable. We'll need a simple initializer, of course, which I'm pretty sure you're comfortable with at this point. We'll also need a function named next that returns an int in order to conform to generator type. The logic herein needs little explanation. Let's create an instance, give it an ending point, and pass it into a while loop. And we see we're getting our next random binary numbers. However, if we try to call rand in a for-in loop, we get an error. In order to create a sequence type, we need a generator type. Having said that, creating our own generator type was merely an exercise, as Swift provides a generic generator for us, any generator of type T. A sequence type is so similar to what we just created that I'm simply going to copy our binary number generator and change a few names. We'll rename our class binary number sequence and make it adapt to the sequence type protocol. Then we'll change the function name from next to generate. We'll change its return type to an any generator with an int. And replace the logic with a closure named any generator. We'll instantiate our object and test our loop as before. And this time we get our binary numbers. To clarify the difference, generator type provides a next value, and we can call next over and over to get our next values. Sequence type utilizes a generator to return a sequence of values that we can simply loop over. In this video, we learned how we can create our own sequence types and generator types. In this section, we looked at how we can create our own extensions. We then learned how we can utilize generics to make our extensions more flexible for ultimate code reuse. We delved into higher order functions, which are a key component to functional programming in Swift. Finally, we looked at how to create our own sequences and generators. In the next section, we'll look at Swift's memory management system and learn how our programming choices can affect our application's memory performance. Hi, welcome to Section 3, where we'll be exploring Swift's memory management system. In the previous section, we looked at functional programming concepts and built out our game-of-life application. In this section, we'll gain an understanding of how the compiler manages memory with automatic reference counting, also known as ARC. We'll spend some time using Xcode's instruments, which can help us to isolate performance issues. We'll also learn about the strong, weak, and unknown keywords, and finally, we'll create some zombies. The first video of this section will gain an understanding of memory management and how Swift's ARC allocates and deallocates memory for you. We'll also see a demo of ARC in action. Memory management is crucial in any application we write. This is due to the hardware limitations of our computers and mobile devices. In the past, developers were responsible for managing memory resources. In the Cocoa world, it was done by means of manual retain release, which is also referred to as just MRR. In MRR, the programmer would declare that an object be kept in memory by claiming ownership on every object created, and then releasing it when the object wasn't needed any longer. The alloc method was used to create an object and claim ownership over it, while retain was used to claim ownership of an already existing object. For brevity, I'll forego further explanation of traditional memory management and instead point you to this video's resource page. To summarize, memory management was tedious, and simple mistakes would cause your application to run out of memory and crash. In 2011, Apple moved to automatic reference counting, which tracks and manages our application's memory usage for us. In most cases, memory management in Swift just works, and we don't need to think that much about memory management. ARC automatically frees up the memory used by class instances when those instances are no longer needed. This shouldn't mean that we ignore memory management altogether, however. As professional iOS developers, we should always be mindful of the relationships between our code and memory. Each time a class is instantiated, ARC allocates a piece of memory for that instance. This piece of memory holds the information relevant to the type of instance, along with any values that are stored in properties associated with that instance. Then, after an instance isn't needed any longer, ARC purges it from memory so that space in memory can be used elsewhere. Of course, if your object was deallocated from memory while still in use by your application, it would crash. To avoid this, ARC uses reference counting to track each of the references to your class objects. As objects are instantiated, ARC increments the number of references to that object. Over time, as references are removed, the count is decremented. To avoid crashes, ARC will not deallocate an instance as long as even one active reference still exists. Once the reference count hits 0, ARC deallocates the instance from memory. In order for ARC to manage these references, it creates what's known as a strong reference each time we store an object. A strong reference tells ARC that it should keep a strong hold on that instance, which forces that object to remain allocated until the strong reference is destroyed. We'll look at these types of references in depth later in this section. We'll start by creating a new single-view application and we'll go ahead and make a new class right away named Vehicle. I'll go ahead and paste this very simple class now. We see we have one property, a simple initializer, and a deinitializer. When our class is instantiated, we'll get an initialization message. When the class is deallocated, we'll get a deinitialization message. This will make it clear to us when our objects are added and removed from memory. Now, in our view controller, let's create some instances of this class. If we run our application, we'll see our car being initialized, but we don't see anything for reference 2. This is because reference 2 is an optional type. It gets initialized with a value of nil, so it doesn't actually have a reference to vehicle type yet. Since reference 1 has a vehicle assigned to it, there is now a strong reference from reference 1 to the new vehicle instance, and Arc will make certain that this vehicle is kept in memory. Let's assign our reference 1 to reference 2, and let's also add a third reference. There are now 3 strong references to this single vehicle instance for Arc to maintain. Now, we'll add a quick modification to this app to support a timer by adding a timer variable at the class level. We'll instantiate our timer inside of our viewDidLoad. And we'll create a function for our timer to fire at a given interval. If we set reference 3 and reference 2 to nil when our timer hits 3 seconds, we'll see that our dinit doesn't fire. However, when our counter hits 5 seconds, our vehicle is finally removed from memory. For more information on Arc, see Apple's documentation, and be sure to watch WWDC 2011, session 323. You can find links to both on this video's resource page. In this video, we learned about memory allocation and deallocation with Arc. We also saw an example of Arc in action. In the next video, we'll look at Xcode's instruments application, which we can use to monitor our memory's performance, issues, and statistics. In the previous video, we looked at how in most cases, Arc manages our memory allocation and deallocations for us. In this video, we're going to take a look at the instruments application. We'll look over the interface, and we'll learn about how both leak checks and heap statistics can help us to visualize our simple application's memory usage. Instruments is a tool that gets installed when you install Xcode on your machine. It's a powerful performance analysis and testing tool that you can utilize to help profile memory and performance issues in your applications. In our last video, we introduced Arc, which handles most of our memory allocations and deallocations for us. However, even the best app designs can encounter occasional memory issues that are difficult to isolate. Instruments can help us to understand how our application uses memory, which makes it easier to identify potential problem areas. Instruments allows us to monitor overall memory use, leaked memory, abandoned memory, and zombies. For more information on instruments, please view this video's resource page. Let's see instruments in action. We'll start by launching Xcode and loading our memory management project. As you'll notice, I've made a small enhancement to this project. I've added a simple button to my view controller so that we can start and stop the application. For convenience, I've included the starter file for this project at this video's resource page. Now that our project is loaded, build and run your application. Before clicking Start on your app, find and click the Show Debug Navigator button. If we double-click the list item named Memory, Xcode takes us to a memory dashboard. Now we can click the Profile and Instruments button, followed by Transfer. This detaches our session from the current running instance and attaches our debug session to Instruments. When attempting to attach instruments to a process, you may find yourself with an error stating that you cannot attach instruments to your simulator with System Integrity Protection enabled. Disabling this feature is straightforward, and if you need instructions as to how to disable this feature, you can look at this video's resource page for a step-by-step guide. This is the Instruments application. Up here, we see the all heap and anonymous virtual memory. The next item down is leak checks. These are just 2 of the many performance profilers available to us. Notice in the leak check swim lane, we see a recurring green check mark. This indicates that our application does not currently have any leaks. And if we double-click on our leak checks, we can see that our leaked objects pane is empty. Let's go back to our statistics pane and then press the Start button on our app. Notice the activity increases in the all heap and anonymous VM swim lane. And after 5 seconds, we see the activity drop, just as we intended with our timer. This is great. We're actually able to visualize our object being allocated and deallocated from memory. You might be curious about this pane down below. This is the statistical allocation summary, which shows us which processes are using memory in our application. We can hover over these items, and we'll see an arrow appear. If we click on one, for example, all heap allocations, we can see the item's details, including the exact address in our object's memory. Now, scrolling through this and trying to make sense of what you're reading might seem futile, and unless you're used to browsing low-level code, it can be. Fortunately, Apple has included a useful search feature to search through this list. If we search for our vehicle instance, Instruments will filter our results and display the log for our vehicle object. Now that we've seen how to locate a potential problem, we have the ability to analyze it further. In this video, we have introduced instruments and visualized our objects in memory. Instruments is a vast and powerful tool for analyzing our application's performance. I encourage you to spend some time with instruments. Becoming better at isolating issues with this tool is key to becoming an excellent Swift programmer. In the next video, we'll look at strong reference cycles and their implication on our application's performance. In the previous video, we looked at Xcode's Instruments tool, and we saw how we could utilize it to isolate memory issues. In this video, we're going to take a look at strong reference cycles and how they can cause memory leaks. We'll then create and identify a memory leak in Instruments. So we've seen how Arc is able to track the number of references, and how when our reference count hits 0, it's able to deallocate our vehicle from memory for us. However, it is possible to write code in which an instance of a class never has strong references. In the following example, we'll see how we frequently create what's known as a strong reference cycle by mistake. Let's open up our previous Xcode project, and we'll add a new class named Driver, which will look like this. We'll create a property that will optionally store a vehicle, and we'll update our vehicle to optionally have a driver. In our view controller, let's add an instance of this new driver object. And we don't need this anymore. Next, we'll add some simple values to our vehicle and to our new driver. So now we have both vehicle and driver instances that contain references to one another. Here's where we'll create our problem. We'll link the two together, which will cause a strong reference cycle. In viewDidLoad, we'll set our vehicle's driver to Steve, and we'll set our driver's vehicle to Car. To visualize, this is how our strong reference looks between our two objects. Here we have created a recursive strong reference. Of course, this strong reference cycle creates a problem for us. When we set both variables Steve and Car to nil, we'd expect Arc to deinitialize our object to free up our memory. But it doesn't. Let's see if we can isolate this problem by running our application in Instruments. Before we do, let's get rid of the timer and update our button logic. We'll replace our NSTimer variable with a simple Boolean flag named toggle. Next, I'll overwrite my button logic with the following. So this is pretty straightforward. The first time we tap the button, we create our objects, and the second tap sets them to nil. We can go ahead and remove this, and we don't need this bit of code anymore. So let's run our application. Again, we'll show the debug navigator and double-click on memory. We'll click Profile and Instruments, and then click Transfer. We'll see our Instruments panel running our application. We see some activity, but we still have our green check marks, indicating that we don't have a memory leak. Next, we'll click the Stop button in our application. And, as we expect, we see a red X indicating we have a problem. If we double-click on our leak checks, we'll see both our driver and vehicle objects. We'll go back to our all heap and anonymous VM pane and run our application again. Click the Display Settings icon and let's click Mark Generation. This creates a snapshot of our application's memory stats. Let's do this several times, creating multiple snapshots with the Mark Generation button. This will compound our problem. Now let's stop running instruments and look at our snapshot. Expanding a snapshot, if we look in the list, we'll see an item named memorymanagement.driver and .vehicle. We can expand those and see their addresses, and we can get even more detail by clicking the Details arrow. In the Details pane on the right, click the Extended Details icon to see the stack trace. Notice these three items in black. If we double-click on one, it'll display the code, and now that we've isolated our problem, we can launch Xcode by clicking on the Xcode icon here. In this video, we have sufficiently created a memory leak by creating a strong reference cycle. In the next video, we'll see how we can fix memory leaks in Swift by utilizing weak and unowned references. In the previous video, we created a strong reference cycle that caused a memory leak in our application. We then saw how to identify the memory leak using instruments. In this video, we'll fix our memory leak problem by utilizing the weak keyword. We'll also look at other use cases for the weak and unowned reference modifiers. In the previous video, we saw a simplified demonstration of a very common scenario. We have a vehicle that has a driver associated with it, and our driver who has a vehicle associated with it. This kind of circular reference is known as a strong reference cycle. This is a simple problem to solve once you know how to identify it. We can do so by simply adding the weak keyword, which tells the compiler that the reference should be weak. A weak reference is a reference that does not keep a strong hold on the instance it refers to, and therefore allows Arc to dispose of the referenced instance. Two conditions have to exist in order to utilize the weak keyword. 1. Both objects need to have independent lifetimes, meaning that they can exist with or without each other. In other words, they are completely independent of one another. 2. The reference has to be an optional or nillable value. Another option to resolve strong reference cycles is to utilize the unowned keyword to mark our reference as unowned. Unowned references work much like a weak reference in which it will not cause Arc to keep an object alive. Unowned references are used for slightly different purposes, however. We use unowned objects when they don't have independent lifetimes. In this example, we see that we have orders and order items. It would make no sense for an order item to exist without an order existing in the first place. It would also make no sense to have an order without an order item, so the order item must be non-nil to utilize the unowned keyword. Looking back at our Xcode project, the weak keyword is the obvious fit for this situation. This should resolve our problem. Let's run our application and then launch instruments. Once instruments is running, we'll tap Run on our application to create some objects and references. Okay, we see a green check mark indicating that we have no leaks. Now let's go ahead and stop our application. Our weak keyword should allow Arc to remove our references. And we get another green check mark. That means we've successfully fixed our memory leak. So we've created a common problem and then resolved it by utilizing the weak keyword. Let's look at another common use case for the weak and unowned keywords. Recall in Section 1, in closure syntax and functional value types, we created a lazy variable that utilized the weak keyword. An important point to note is that a closure is an object that can contain strong references within its scope and that can continue to exist after the closure has finished executing. Specifically, if a variable within the closure scope has the self-reference, it points back to our life object, creating a circular reference. So, consider what's happening here. Our lazy var's self-reference is pointing at life, and life has a reference pointing at our closure. We need a way to tell Arc that one of these references is weak or unowned. We're doing that with our closure's capture list by adding weak self in to the beginning of our closure. In essence, we're telling the memory management system that our references to self are to be weak. Every time we use a closure that has a self reference, we must have a capture list that has a weak or unowned self reference, or we'll get a memory leak. This is an extremely important point to remember about closures. So we can address memory leaks in Swift by breaking our strong reference cycles with weak and unknown self-references. Judging by the simplistic examples I've shared, one might conclude that resolving memory issues is always a straightforward and easy process. It rarely is. Usually, strong reference cycles are created inside large, complex systems and can be terribly difficult to track down. The only true way to combat this is to always ask yourself, am I creating a strong reference cycle or a circular reference when you are creating references to objects? In this video, we have resolved our memory leak and visualized its resolution in instruments. In the next video, we'll create a memory zombie. In the previous video, we resolved a leak by utilizing a weak reference modifier. In this video, we're going to learn about how zombies can occur while interoperating with C and Objective-C. We'll finish this video by creating a zombie of our own. Zombies occur when we over-release an object by deallocating it more than once, or when we reference an object that has already been deallocated. When using Swift alone, zombies aren't really an issue, but since we, as iOS professionals, may one day be tasked with interoperating with C or Objective-C, we should understand the risks. Let's begin by creating a new Xcode project. Choose a single view application, name it Zombie, and click Create. Open up your storyboard and create a button similar to the last video. And change the label if you like. We'll drag out an action and name it Handle Create Zombie Tapped. At the class level, declare a variable with the type of unsafe mutable pointer of type string. I should probably take a moment to describe what this unsafe mutable pointer is. This structure is a generic unsafe mutable pointer that takes a type of T. This generic wrapper provides interoperability from Swift to this native C type. We use this type when we want to manage memory pointers manually, which in turn means that if we don't manage it correctly, we can cause leaks or even crashes. For more information on this topic, visit this video's resource page. Once we've created our unsafe mutable pointer, we'll add the following lines to our viewDidLoad. The first line allocates a space in memory for our string. The next line initializes our value to faucet. And next, we set our variable to nil. If we left our program as is and ran it, we'd create a memory leak since we haven't destroyed and deallocated the object before setting it to nil. To avoid a leak, we'll start by moving our nil assignment up to our Handle Create Zombie Tapped action, and then we'll insert 2 lines just above it. This first line deinitializes our object, much the same way as we can deinitialize an object using a deinit method in a class. The next line here actually performs the deallocation. This is what Arc actually does for us when our reference count hits 0. This code is now properly deallocated, and as is will not cause an issue. Now let's create a zombie. Just duplicate your dealloc line and place it below the original. Let's build and run our application. Once your application is loaded, let's tap Create Zombie to see what happens. The application crashes and it shows us right where the problem is. This is one method of creating a zombie. Let's see how this looks in instruments. We'll need to change a few settings in Xcode before we can get instruments to report on zombies. Click on your active scheme. When the dialog appears, select Enable Guard Malloc, Enable Zombie Objects, and Stop on Debugger and Debug Stir. Then click Close. Run your application and, just as before, let's click Memory in our Debug Navigator and then click Profile in Instruments and Transfer. We see our application running fine. Recall that our object was created on launch. Now, when we tap Create Zombie, our application will crash and Instruments will report the NSZombie leak. The second way to create a zombie is by trying to reference the deallocated object. In order to test this, you can simply remove the second dealloc call and replace it with an assignment call like this. Again, this is something that you're unlikely to encounter in Swift unless you're working directly with Objective-C or C. In this video, we have created a zombie and saw how we can detect it in Instruments. In the next video, we'll look over 8 tips to improving memory performance in our applications. In the previous video, we learned about zombies and how they're created so we know the risks of manual memory management. In this video, we're going to look at 8 things you can do to improve memory performance. We'll look at what we should avoid and what we should know before making programming decisions. 1. Use lazy loading when appropriate. You may feel the impulse to load all of your resources into memory when your application loads, so that your data is always available when your user needs it. Preloading data in this way may come with the side effect of a sluggish initial user experience. Keep in mind that most people only use their mobile devices in short bursts, often less than 30 seconds. That said, you may be loading data into memory that's not crucial to the user's session. Rather than loading your data on application startup, you should be using lazy stored properties whenever possible. A lazy stored property, as you know, is a property whose initial value is not calculated until the first time it's accessed. So, if you need to create objects, retrieve data from a cache, or import data by some other means, you should consider using a lazy property. 2. Reduce reference counts with optionals. Optionals allow you to set your object's value to nil, which lowers the reference count of classes. Setting your objects to nil when you no longer need them is the easiest way to clean up memory. This works hand in hand with Arc. As you set your unused objects to nil, your instance's reference count decrements. When your counts reach 0, of course, Arc will deinitialize and free up memory. 3. Break strong reference cycles by using weak or unowned. We've covered this topic at length earlier in this section, but we'll briefly recap. When creating recursive references between classes, or when using self inside of a closure, make sure that you either use the weak or unowned keyword to break the strong reference, allowing Arc to deinitialize your instance. 4. Proper casting reduces instance counts. While some operations don't have an impact on memory usage, others do. For example, we can change a value's type from its original type into another type by passing it into the new type's initializer. When we change types this way, we're creating a new instance of the object, which has memory implications. Instead, make sure to utilize Swift's as keyword to cast your values to a new type whenever possible. Casting does not create a new instance, nor does it have the same memory implications. 5. Understand the difference between reference types and value types. We discussed this somewhat in Section 1, but it's an important facet to programming in any language we encounter, so we'll reiterate here. Both reference types and value types have their own advantages and their own dangers. Structs and enums are value types, which means they are copied rather than referenced, which can be more memory intensive since they are copying their values each time they are assigned to another instance, effectively doubling memory usage. Now the trade-off is that copying them allows them to be accessed directly, which of course is optimal for thread-safe performance. Classes, as we've already discussed, don't behave this way because they are reference types. This means they don't copy when they are assigned. Instead, they create another reference for Arc to track. 6. To avoid creating copies, utilize inout. Functions capture the values passed into them by creating new copies. However, Swift offers an inout keyword. Inout allows us to pass an object into a function and modify the original rather than creating a new copy. This has the ability to improve memory performance depending on what you pass in and what type of operation you're performing inside your function. 7. Avoid unnecessary caching. Caching frequently accessed items is an excellent way to provide immediate data to your user, which can enrich the user experience. Caching is often the right choice, but keep in mind that NSCache and other caching libraries will usually discard parts of the cache when you're running low on memory, causing potential issues down the road. 8. Know the benefits of object-oriented programming over functional programming. Remember that functional programming uses immutable states, meaning that certain operations can be devastating on your memory. In some cases, it's best to utilize OOP's mutable states to reference one instance rather than creating new ones. In this video, we looked at 8 approaches to improving your memory performance. One could easily spend hours investigating each one of these techniques, and one absolutely should. If you take the time now to make sure you fully understand how memory works, you'll save yourself countless hours in troubleshooting and debugging over the course of your career. In this section, we've learned about the allocation and deallocation of memory. We learned about Swift's ARC memory management system. We also introduced Xcode's instruments tool and isolated both memory leaks and zombies. In the next section, we'll learn how to include frameworks into our application and how to make Swift play nice with both C and Objective-C for interoperability. Welcome to Section 4, where we'll discuss interoperability and working with third-party libraries. In the previous section, we saw how to improve the performance of our applications by understanding how memory is managed in iOS and by learning how to find and fix potential issues. In this section, we're going to learn how Swift implicitly bridges to Objective-C with the Cocoa framework. Then, we'll learn how we can utilize bridging headers to enable our Swift code to communicate with Objective-C, C, and even C++. We'll also see how we can utilize CocoaPods to incorporate third-party libraries into our applications. Now we'll move on to the first video of this section, Implicit Bridging and Cocoa, which illustrates how Swift to Objective-C implicit bridging works. In this video, we're going to take a look at some similarities as well as some differences between Objective-C and Swift syntax. We'll see how each one utilizes the same Cocoa framework and how Swift types can implicitly bridge to Objective-C. Swift is a powerful, fast, and safe programming language that brings a lot of modern language features to the Cocoa framework. This, to many, has been a big sigh of relief for developing iOS and OS X applications. Unfortunately for Swift developers, the vast majority of OS X and iOS applications were written in Objective-C, and if you're planning on working as an Apple platform developer, you'll have to know how to interoperate with, at bare minimum, Objective-C. Swift provides seamless access to Objective-C's APIs, mapping all of your Objective-C code directly to Swift syntax. And since both Swift and Objective-C utilizes the same Cocoa framework, there's a lot of inherent similarities between the two. However, syntax is not one of them. Let's look at some examples of the implicit bridging that we get for free with Swift. Here we have Objective-C's UI document class, which we'll break down piece by piece. We'll start with the file modification date property, which is of type NSDate. In Swift, this declaration would look like this, which in Objective-C translates to this. We see our properties are defined with the @property keyword, followed by the type, and then the named pointer. We see here that Swift utilizes a forced unwrapped NSDate optional. This is because Objective-C doesn't contain the notion of an optional pointer. So, in order for Swift to use NSDate in the same manner as Objective-C, it needs to be explicitly unwrapped. Of course, there are mappings for all of Objective-C's other types as well, though unlike NSDate, most have slightly different syntax as shown here. Notice that ID gets mapped to an any object, and class gets mapped to any class. Methods are a little less straightforward. Here we have a Swift method, file name extension for type, and again the same method in Objective-C. Although the syntax is quite a bit different, we can see that these are clearly the same methods. Here, the name for our method is the same, along with the first and second labels and their types. And we have our return types. This is pretty straightforward. It does get a bit more complex, however, when we introduce blocks. Here we have a UI document saved to URL method in Swift, and again in Objective-C. Swift's version is a bit cleaner. Here we have the external and internal labels, along with a less redundant completion handler argument. The big difference, however, is in the completion handler, which is called a block in Objective-C. Objective-C's blocks are bridged into Swift closures for us, which allow us to use Swift's modern trailing closure syntax. NS errors are an interesting case because Swift, in many cases, completely does away with the error argument and introduces a new feature to deal with errors. In Objective-C, returning a nil value represents a failure case. In that case, the outError parameter is populated. In other words, if our NS error parameter comes back non-nil, we know we have a problem. Swift removes the error parameter altogether and utilizes the new throws keyword, which tells us that the method has the ability to throw an error. Functions marked with throws should be called within a try-catch block to handle the error should one arise. We'll be looking closely at error handling in Section 6, Troubleshooting, Advanced Debugging, and Error Handling. By now, I'm sure you've noticed that Swift brings with it much cleaner and more succinct syntax than its Objective-C counterpart. We also see that the init methods are no exception. Notice that Swift removes the with file URL and instead sets file URL as its argument label. This is a consistent convention throughout Swift. If you ever need to convert an initializer from Objective-C, remember this pattern. Let's look at one last example before we move on to some demonstrations. Enums in Objective-C are declared as follows. Again, the same enum maps to Swift with a much cleaner syntax. Now that we've looked at how Swift's implicit bridging works, let's look at some examples of how we can expose Swift to Objective-C code and how we can use Objective-C in our Swift code. In this video, we looked at some of the similarities between Objective-C and Swift, and how they implicitly bridge to utilize the same Cocoa framework. In the next video, we'll briefly discuss how we can expose our Swift code to Objective-C. Then, we'll see a demonstration of how it's done. In the previous video, we learned how Swift utilizes implicit bridging to work with the Cocoa framework. In this video, we're going to see how we've already been exposing our Swift code to Objective-C. Then, we'll create an Objective-C project and call some Swift code from Objective-C. Assuming that you've been working in Swift for a little while, you've been exposing bits of your Swift code to Objective-C all along. For example, if you've ever utilized an IB outlet or an IB action or NS managed, you've been working with Objective-C. Furthermore, if you have a class that is a subclass of NS object, then by default, the entire class is exposed to Objective-C. In this example, we see a familiar class that subclasses UIViewController, which indirectly subclasses NSObject. So these NSObject methods and properties will be exposed to Objective-C. However, functions and properties that use Swift-only features will automatically be ignored by Objective-C. Of course, you can limit your properties' visibility to just Objective-C by labeling them as private, which will make them visible only to the containing class. To more deliberately expose your code to Objective-C, you can utilize the @obc keyword on your properties and methods. On the other hand, you can also use the non-obc modifier to limit your code's visibility to Swift only. Let's create a simple Objective-C application that runs some Swift code. Open up Xcode and create a new project. Choose iOS application and single view application. Name it anything you like and make sure you change your language to Objective-C. Click Next and then create your project. Let's start by adding a Swift file to our application. Click on your root directory and press Command-N, select iOS source, and choose Cocoa Touch class and click Next. Name your class Hello from Swift and add a subclass of NSObject. We'll select Swift as a language and then click Next and then Create. You'll be prompted with a dialog asking if you'd like to create a bridging header. Click Don't Create. We're not going to be working with a bridging header manually because Xcode will generate an umbrella bridging header for us. All we need to know is how to import the generated header, which we'll do momentarily. In your Swift file, name your class Hello from Swift. We'll create a variable named message and give it a default value of from Swift. Next, we'll create two initializers, one override initializer that calls superinit, and one required initializer for our NSObject class, which also calls superinit. Finally, we'll add a method named getMessage that simply returns our message variable. There are a few build settings we need to change before we start with our Objective-C code. Click on your root project and select your application under Targets, and then select Build Settings. In the search bar, search for Embedded Content Contains Swift Code and set it to Yes. Then, search for Install Objective-C Compatibility Header and set it to Yes as well. Finally, search for Defines Module and set that to Yes. Now that we have our build settings in order, let's open viewcontroller.m and call our Swift code. At the top of your class, an import statement for our auto-generated bridging header. The auto-generated header starts with your project name, then a hyphen, then swift.h. Now let's create a class instance. Right away we're getting errors. While NSObject makes Swift available to Objective-C, our Swift class inherits an access modifier of internal, which makes it invisible to Objective-C. Let's mark our class, variable, and function as public. And we see our class instance is now valid. Let's try printing our message variable to our console. Declare an NSString variable and name it message and set it equal to hello.message. Let's use an NSLog to log it to the console. Build and run, and we see our Swift message print to the console. Again, if we change our access modifiers on our variables to private, we lose the ability to call that variable directly from Objective-C. We can still print our message, though, by calling our Swift function. Let's change the value assignment to our variable from hello_message to hello_getMessage. Build and run your application, and again, our message prints to the console. In this video, we have successfully called Swift code from Objective-C. In the next video, we'll see how to call Objective-C code from Swift. In the previous video, we went over how to call Swift code from Objective-C. In this video, we're going to take a look at how we can utilize bridging headers to call Objective-C from Swift. Let's get started by creating a new Xcode project. We'll change it up and create a command line tool under OS X. We'll name our project Objective-C in Swift, and select Swift as our language and click Next. Choose a place to save and click Create. Let's start by creating our Objective-C code. Press Command-N to create a new file. We'll select the Objective-C file, name it Fibonacci, and click Next, then Create. Xcode will ask us if we want to create a bridging header. Select Create Bridging Header, which we'll use to bridge to Swift. In our Fibonacci.m file, we'll create a simple interface named Fibonacci with NSObject as a subclass. We'll define a single function named calc that takes an int and returns an int. Now let's move on to our implementation. We'll add a simple init function, then, for brevity, I'll paste in the calc function. We see our function takes an int and returns an int as defined in our interface. Now, if you've never seen a Fibonacci generator before, it's a function that recursively calls itself to generate Fibonacci numbers. You can find a detailed breakdown of how this function works on this video's resource page. We'll be calling this Fibonacci generator from our Swift code. Now let's open our bridging header file and we'll add a simple import statement. We'll write import Fibonacci m. Let's open our main.swift file and create an instance of our Objective-C Fibonacci class. We'll create a constant named fib and give it a value of Fibonacci. Then, we'll create another constant named calc and give it a value of fib.calc30. Finally, we'll create a print statement that prints our output to the console. Build and run, and you should see your Fibonacci calculation in the console. This is pretty neat, but let's build something a little more interesting based on what we've learned in Section 2. Let's use our Objective-C Fibonacci class to create a sequence type in Swift. Create a new Swift file named randomFibs declare a class name randomFibs, and we'll subclass our Objective-C Fibonacci class, which will give us immediate access to our Objective-C code. Then, we'll also implement the sequence type protocol. We'll define two properties at the class level. The first property, number of fibs, will be the quantity of Fibonacci numbers the user asked for. The next property is a simple counter that will initialize to 0. We have a simple initializer that allows the user to input their desired number of Fibonacci calculations. Then, we have our mandatory generate method that returns an any generator of type int32, which satisfies our Objective-C method's parameter. We also have a guard check that will stop the process by returning nil when we hit the user's desired count. Next, we increment our count, create a random number, and finally, pass the number into our Objective-C method. Now, let's update some code in main to call our new class. We'll delete what we have already and start by creating an instance of our randomFibs class and pass it a value of 5. Now that we have a sequence of randomFibs, let's iterate over them to see what values we get. I'll implement a simple loop and put a print statement inside. Build and run, and we see we have 5 random Fibonacci numbers that were generated using Objective-C code. You've just opened up a whole world of possibilities. Now that you know how to incorporate Objective-C into your Swift applications, you can take advantage of the countless useful Objective-C libraries available to you for free. In this video, we have successfully bridged our Objective-C Fibonacci generator to Swift. In the next video, we'll demonstrate how we can use standard C code in our Swift projects. In the previous video, we learned how to incorporate Objective-C code into our Swift projects. In this video, we're going to take a look at how to convert C types to Swift types and what it takes to incorporate traditional C code into our Swift projects. There are a few things to keep in mind when working with C, particularly when working with C's types. C has numerous types for scalars such as booleans, characters, and numbers. These types can be of different widths, as C offers 32 and 64-bit integers. Swift scalar types will not automatically convert to C's types. For example, a C int and a Swift int are not equivalent, so when passing values to a C function, we need to either use an int32 or a C int. Fortunately, the Swift team thought of this and provided C equivalent types in Swift. I'll make this chart available to you on this video's resource page. As we saw in Section 3, we can also use C pointers in Swift. Pointers are a notorious pain point for developers and one of the biggest sources of bugs, which is why the Swift team abstracted pointer and memory management away from the developer. Remember, Swift is a safe language. That said, Swift does provide a way for developers to interoperate with C pointers, which is by using the generic unsafe pointer types as shown here. Of course, you can find more details on how Swift interoperates with C on this video's resource page. Let's move on to an example. Create a new Xcode project, and let's create an OS X console application. Choose a name, and select Next, and then Create. The first thing we'll need is to add a new C file. With your root directory selected, press Command-N and create a new file. Select C file and press Next. I'll name my file Math and click Next, and then Create. When the application asks if you'd like to create a bridging header, select Create Bridging Header. We'll start with a C header file named math.h. This is where we declare the functions that we'll be implementing in C. We'll add 2 functions, one named multiply and one named square. The xturn keyword tells the compiler that this data is defined somewhere and will be connected with the linker. Then we have our return type, followed by our function name and parameters. Let's move on to our .c file. We'll implement the 2 functions that we just declared in our header file. We'll name the first function multiply, which takes 2 ints, x and y, multiply them, and then returns a single int. Our second function, named square, takes an int, squares it using C's pow function, and then returns the product. Finally, we'll configure the bridging header, which couldn't be more straightforward. Just add an include statement and include your header file, math.h. Now let's go ahead and call these functions from Swift. In main.swift, let's create a constant named val that's of type int32 and give it a value. Then we'll create another value named output and set it equal to our square method, and we'll pass in our value. Let's print our output with a simple message and build. And we see our values have been squared by our C code and printed to the console. Let's add our multiply function to the mix. We'll pass in our value and the output from our last C function call. We'll update our print statement with our new constant name and build. Again, we see our expected output. This is excellent. You now have the ability to interoperate with powerfully fast C-based libraries. Let's go find a simple C program on GitHub. Navigate to github.com and we'll search for obfuscated game of life. This is the project we're looking for. It's Sean Murray's contest submission for the International Obfuscated C Code Contest, where he submitted a brilliantly obfuscated version of Game of Life. Click on his life.c file, and we see some wildly difficult to read C code. We'll borrow his code for this exercise, and while we're at it, we'll make sure we star his repository. Now, we could make a brand new C file and a new bridging header for this, but I'll just add it to our existing files for brevity. I'll change the name of this program to Game of Life and switch the return type to void. And then we'll add a reference to our header file. We'll comment out our code in main and make a simple call to Game of Life and run our program. And we see Game of Life carried out in our console. In this video, we have successfully bridged C code with our Swift code. In the next video, we'll discuss C++ interoperability with Swift. In the previous video, we learned how to use C code in our Swift projects. In this video, we're going to take a look at how we can work with C++ without direct C++ interoperability. While we can't call C++ directly, we can utilize what we've learned in our last few videos to wrap C++ in Objective-C, which we can call. For the most part, OS X and iOS projects are mostly written in Swift, Objective-C, or C, which is part of the reason why Swift's team made interoperability with those languages easy to do. While direct interoperability with C++ is in Swift's future, it will not be making it into Swift 3. This is unfortunate because there's a lot of great C++ libraries and APIs out there that would enhance a Swift developer's toolset. So one might wonder why direct C++ interoperability was excluded in Swift. Direct interoperability with C++ is a big challenge because C++ itself is a very complex language. For the Swift team to provide interoperability in the way that they have with Objective-C and C would be a mammoth undertaking. There are two approaches to calling C++ code from Swift. The approach that we'll be using here is by simply using C++ code inside of an Objective-C++ file. The second approach is by wrapping C++ code in C and then calling the C code. I'll provide a walkthrough guide on this video's resource page for those interested in learning the second approach. So we'll start by creating a new Xcode project. We'll make another OS X command line tool, and we'll name it Hello from CPP, and we'll click Create. The first thing we're going to do is add a new Objective-C file to our application. We'll name this file Hello from CPP as well, and click Create. We'll allow Xcode to create our bridging header for us. Next, we'll rename our file from hellofromcpp.m to hellofromcpp.mm, which turns our Objective-C document into an Objective-C++ document. Next, we'll add a new header file with the same name. I'll go ahead and paste in the interface for our implementation. So here we have an interface for our implementation called Hello from CPP that contains one function that takes an NS string and returns void. Next, we'll open our hello from cpp.mm file and paste in the implementation. As we can see, we're importing our header file and then following our interface. We have an implementation of hello from CPP that contains one method named hello from CPP that takes an NS and returns void. We can see that our hello from CPP method has some C++ code that simply prints the word hello followed by the string that we pass in. The next step is to update our bridging header to import our new hello from CPP header file. And with that, we should be able to call our Objective C++ method. Back in our main.swift file, simply add a new instance of hello from CPP, and then call the hello from CPP method from the instance and pass in whatever string you like. Build and run the application, and you'll see your message printed to the console. This is one way of working with C++ from Swift. Again, I'll share another way to do it on this video's resource page. In this video, we have seen how to incorporate C++ code in our Swift projects. In the next video, we'll look at a popular package manager called CocoaPods. We'll utilize CocoaPods to install a third-party library. In the previous video, we learned how we can utilize C++ in our Swift code. In this video, we're going to discuss package management, third-party libraries, and how we can utilize CocoaPods to install libraries and frameworks into our projects. There are a couple of popular ways to import libraries and frameworks into your project. They each have their advantages and disadvantages, and no current solution is perfect. I should mention, however, that Apple has announced their own dependency manager called Swift Package Manager, which has a lot of developers very excited to move to something better. The bad news is, as of this recording, the Swift Package Manager doesn't yet support iOS. Currently, the most popular dependency manager is CocoaPods, which is what I'll demonstrate here. We're going to enhance our Game of Life application with the ability to connect to a server to post and receive high scores. We'll utilize CocoaPods to install Alamo Fire, which is a sleek and popular alternative to Swift's native NSURL session. We'll start by installing CocoaPods if you haven't already. Open up a terminal by pressing Command Space and then entering Terminal into search. Once Spotlight finds Terminal, hit Enter and Terminal will launch. Before I get started, what I'm about to demonstrate will alter your file system, so please do so at your own risk. Having said that, if you do encounter issues, you can visit this video's resource page where you'll find troubleshooting tips. You'll also see a comment section. You can leave a comment and I'll try to help. With Terminal open, type sudo gem install CocoaPods, which will install in Ruby inside your OS X system library. Once complete, type pod setup -- verbose, which may take a few minutes as it clones the CocoaPods master specs repository to your computer. The verbose option logs progress as the process runs rather than showing you a static or seemingly frozen screen. With CocoaPods installed, we can now add a pod file to our project. Assuming that you've got your project on your desktop, we'll navigate to our project folder using Terminal. Type ls and then press Enter to list your initial directory. You should see Desktop as one of your options. Next, type cd desktop and press Enter to navigate to your desktop. Once there, type ls and press Enter to list your desktop contents. On my desktop, we see Game of Life, which has some spaces which require escaping in Terminal. Fortunately, we can use the Tab button to get Terminal to auto-complete our directory name for us. Type cd game and then hit Tab, and you should see cd Game of Life printed for you, and hit Enter. Now that we're sitting at our project's root directory, we can install our pod file by typing pod init, which will initialize pods for this project. After your pod is initialized, type open-a Xcode pod file and hit Enter. This will open your pod file in a plain text editor for you. Next, we'll navigate to the Alamo Fire GitHub page for directions. Once there, scroll down until you see this bit of code here and copy it. We'll add it to our pod file between do and end. Before we save and close, let's look at this pod file structure. At the top, we see a target which points to our Game of Life application. Next, we see source, which specifies the location where the library or framework should be retrieved. Then we have platform, Here we place the lowest supported operating system version, in this case iOS 8. Next, we have Use Frameworks, which tells CocoaPods to install this package as a Swift framework rather than a Swift library. There are several benefits to using frameworks over libraries. The most obvious is that libraries are usually only the executable code, while frameworks offer a bundle with a directory structure that include additional resources like documentation, assets, and configuration files. Finally, we see the pod followed by the pod name we're going to install and the versioning. Now, back in Terminal, we'll enter pod install, which installs Alamo Fire into our project. Once complete, you'll see a similar screen. Now, we'll open up our project using our new workspace that's generated by CocoaPods. Open your project folder on your desktop, and then click on the new file with the white icon ending in .xc workspace. We'll be working from this file from now on. Open your view controller and add Import Alamo Fire at the top. You'll notice that Xcode complains. This is because we haven't linked this library yet. To do so, we'll click on our project's root directory. Then we'll select our application under Targets and select Build Phases. Under Link Binary with Libraries, we'll add Alamo Fire, which should resolve our error in Xcode. Although we will be using Alamo Fire in upcoming videos, we won't be covering the Alamo Fire API in great detail, since it's not the focus of this course. I'll make sure to add some example usage to this video's resource page. In this video, we have successfully installed CocoaPods and then used CocoaPods to add Alamo Fire to our Game of Life application. In the next video, we'll incorporate an Objective-C library manually. In the previous video, we saw how CocoaPods can manage our third-party dependencies for us. In this video, we're going to see how we can incorporate a third-party library into our application manually. Then we'll interoperate with Objective-C to implement the framework as the author had intended. So we've learned a bit about interoperability, and we've added a CocoaPod to our Game of Life application. Not all libraries require a dependency manager like CocoaPods. In this video, we'll add an Objective-C library called swRevealViewController to our application manually. This library will allow us to create an interesting sidebar menu for switching views, which will come into play during our next section, where we'll discuss asynchronous programming and concurrency. We'll start by navigating to GitHub and searching for swRevealViewController. The top result by John Lutch is the repository we're looking for. Once his page loads, click Download Zip and download his project. Next, we'll open up our Game of Life application, and then we'll navigate to our freshly downloaded library. There are quite a few files in this folder, but what we're looking for is this folder here named swRevealViewController, and we're looking for these two Objective-C files. Drag them into your application and select Copy if needed, and click Create Bridging Header. Now that we have the files copied into our application, let's start implementing our sidebar menu. Drag a new view controller out onto your storyboard. Next, we'll set it to isInitialViewController, and I like to set my size class to 4.7 inch to save horizontal space. Let's set our class in the Identity Inspector by selecting swRevealViewController from the Class drop-down menu. Next, we'll create a static table view controller that will represent our menu. Again, I'll set it to 4.7 inches. Then, in the Attributes Inspector, set the content to static cells. This starts us out with 3 static cells for our game. We'll click on Table View Section in the document outline and set the number of rows to 4. We'll leave our first cell blank to give us some padding at the top. Then we'll add labels to the remaining cells. And then we'll name our second cell Life, which will load our game. Our third cell will be named Most Iterations, which will display the records for the games that had the most iterations to complete. Lastly, we'll name our fourth cell Least Iterations, which will display the records for the lowest number of iterations to complete. If you haven't guessed, we'll be using Alamo Fire to upload our high scores and low scores to a server. and will display the least and most iteration scores along with the username. Next, we'll connect a custom segue from our Reveal View controller to our menu by control-dragging from the yellow View controller icon to our menu controller. And we'll choose SW Reveal View Controller Segue Set Controller from the options. Then, with your new segue selected, we'll set our storyboard segue to SW_rear. This tells SW Reveal View Controller the stacking order of our views. Now we need a front controller. An obvious candidate is the main application, so once again, we'll control-drag from our Reveal View Controller, but this time to our Game of Life View Controller. Again, we'll use Set Controller in our segue, but this time we'll set our identifier to SW_front. In order for us to open and close our menu, we'll need to add some sort of button to act as a toggle for our menu. Let's utilize a navigation controller to accomplish this. Select your main Game of Life controller, and then go to Editor in your File menu and find Embed In, then select Navigation Controller. With that, we can easily add a bar button item for our menu toggle. Go to your object library and search for bar button item. Once you find it, add it to your left bar button items area and name it Menu. Next, we'll open up the Assistant Editor and make sure the View Controller code is showing. We'll control-drag an outlet from our newly added button to our View Controller, and we'll name it Menu Button. Finally, we'll add the following lines to our ViewDidLoad. Here, we're checking to see if our View Controller does have a Reveal View Controller instance. If it does, we'll set our menu button's target to self.revealViewController, then we'll set the action to Reveal Toggle. Here, we are calling a method in the SWRevealViewController library that actually fires the toggle. The next line adds a pan gesture recognizer, which allows us to use swiping to open and close the menu. Last, we're defining the width, which is the distance that the front view will displace to show the menu. I've chosen 200, but you can set this number to whatever you like. We see that our application is complaining. Can you guess why? We haven't set up our bridging header yet. So, while Xcode is aware of SWRevealViewController, our application is not. Let's update our bridging header with an import statement for SWRevealViewController.h. And that should do it. Build and run, you should see your menu in action. In this video, we have seen how to manually incorporate a third-party Objective-C library into our application. In this section, we looked at how Swift and Objective-C work with the Cocoa framework. We learned how we can interoperate with legacy Objective-C code bases and learned how we can utilize both C and C++ in our projects. In the next section, we're going to take a look at asynchronous programming, concurrency, and Grand Central Dispatch. Hello. Welcome to Section 5, Concurrency and Grand Central Dispatch. In the previous section, we learned how to interoperate with other programming languages and add third-party libraries to our applications. In this section, we're going to learn about what concurrency is, and we'll learn how to manage our code using threads, operation queues, and Grand Central Dispatch. And now we move on to our first video of this section that introduces you to the concept of concurrency. In this video, we're going to take a look at how concurrency evolved from perceived parallelism to true concurrent parallelism. We're going to emphasize on learning concurrent programming as well as understanding thread management. Before we discuss how to manage our own concurrency, let's explore exactly what it is and why we need it. Concurrency is the process by which a computer or program can perform multiple tasks simultaneously. Consider the case of a computer with a single processor. In the 90s, all consumer-end computers had just one processor and could only execute one thread at a time. Even with just one core, we were able to run multiple applications in near parallel to each other by having the processor rapidly switch between each running process. Now, running each program for such short periods of time may seem terribly inefficient until you consider that modern processors can execute several billion instructions per second. So even if each program is only run for 1 millisecond, it can execute over 1 million instructions. As technology improved, chip manufacturers continued to release faster and faster single-core chips, which enhanced the perception of parallelism. Eventually, however, chip manufacturers hit a physical limitation on the possible clock speeds, and ultimately compensated by releasing CPUs with multiple cores. Multiple processor cores means that the computer can execute multiple tasks at the same exact time. This means no more perceived parallelism. So, as programmers, we find ourselves in a multi-core world, where even our smallest devices have multiple processor cores in them. In turn, most of the applications we use and create utilize multiple threads of execution. This allows our applications to remain responsive when performing time-consuming operations such as processing images, communicating with remote servers over a network, reading a large dataset from a file, to name a few. So, what exactly are threads? A single application often has multiple paths of execution. These paths are known as threads. Each thread represents different computational tasks that are scheduled independently by the operating system. So threads are what allow our programs to perform several tasks at once. Once we queue a task on a thread, it is not immediately run, but rather it's scheduled to run by the operating system. So we have no guarantee as to when or in what order our tasks will actually run. It is important to understand that our program's threads are not isolated from one another. They share memory space, data sets, and even communicate directly with each other. Since there is no isolation between threads, this means that each thread is capable of interfering with the memory of other threads, allowing them to change the values before the tasks are completed. This can result in what's known as a race condition, which, as I'll demonstrate in the next video, is a condition where two or more threads are accessing the same data structures, resulting in undesired behavior. So, having said that, we must take care while managing our own threading. For more general information on concurrency, make sure to see this video's resource page, where I'll share some more insights and links to external resources. In this video, we saw how modern parallelism came to be and learned a bit about threads. In the next video, we'll continue our conversation about threads with an example using NSThread. In the previous video, we discussed concurrency and how threads have the ability to mutate each other's values in undesirable ways. In this video, we're going to take a look at the NSThread class and how we can utilize NSThread to queue up tasks for the system to schedule. We'll also demonstrate how two threads can interfere with one another if used improperly. The Foundation framework provides a class named NSThread, which greatly simplifies the creation and management of new threads in our programs. While NSThread manages the setup and disposal of threads for you, it does not provide any protection from other threads. Let's start by creating a new Xcode project. We'll select OS X application and create a command line tool for this example. Add a name for your project and click Next. Choose a place to save and click Create. We'll start by making a class that has a single property that will hold our current value, and then a function that will increment that value from 0 to 5,000 and then decrement back to 0 again. I'll create a class named Threading. NSThread utilizes the Objective-C perform selector, so we're going to need to expose our class to Objective-C by either subclassing NSObject or by using the obc keyword. In this example, we'll simply subclass NSObject. Now that we have our class defined, I'll add a property and give it a value of 0, and for brevity, I'll paste my function in. This rise-fall function has two for each loops. The first iterates over a range from 0 to 5,000, and then increments our counter accordingly. The next for each loop decrements our value back to 0. Now, I could have done this example with just one for loop, of course, but I wanted to give our threads more opportunities to intermingle. Now that we have our threading class fleshed out, we'll add a new variable that will hold an instance of our threading class, and then we'll call our rise-fall function, build and run, and you'll see that your program quickly returns 0, as to be expected. No matter how many times we run this function, we'll always arrive back at 0. We can even add subsequent calls to our rise-fall function, and as we see in our console, we always arrive at 0. This is because our rise-fall function performs our loops synchronously, meaning that when our first call to count.risefall is made, our application waits until it completes before making the second call. This is because both of our calls are operating on the same thread. Now, we can move our second call to rise-fall off of our main thread and onto its own thread to call this function concurrently by using the NSThread class from Objective-C. So let's create an instance of NSThread and call the detachNewThreadSelector method, which takes a selector, a target, and optionally an object. So for our selector, we'll call our rise-fall method, and we're going to target our count instance of our threading class object, and then we won't be passing an object, so we can just set that to nil. Now NSThread runs asynchronously, meaning that when we call it, it doesn't wait for its operation to complete before our run loop fires our count.risefall. Since we can't guarantee that our NSThread will finish first, our main thread has the potential to finish first and end the loop before our NSThread has completed its operation. To mitigate this, we'll add a call to sleep and pass it a value of 1, which will allow both of our threads to complete their tasks before ending the loop. Let's go ahead and run this. And as you might have expected, our count is off. I'll run this a few more times, and while I do, notice that the values are different every time. This unpredictable behavior is happening because our threads are both accessing the same values and incrementing and decrementing them asynchronously. Here, we have our main thread running our loops synchronously. Notice that our first instance gets called, and our values are incremented and decremented before the next instance gets fired. Now let's add a second thread to the mix. Notice that our first instance call starts, and almost immediately after, our next call begins its work, both operating on the exact same object. In this video, we looked at how our threads can intermingle and disrupt our expected output. In the next video, we'll demonstrate how we can force our loops to behave as expected by implementing locks. In the previous video, we saw how one thread can disrupt the predictability of our code by updating another thread's values. In this video, we're going to see how locks can fix this issue by disallowing concurrent multi-threaded access to small bits of code. We'll start by opening our previous project and build and run right away to see the issue at hand. So, the problem we're facing is that we're running two threads concurrently and we don't have any isolation between them, so their operations are updating our value out of sync. We're going to address this by introducing NSLock. An NSLock object is used to coordinate the operation of multiple threads of execution in an application. We can use NSLock, which utilizes standardized POSIX threads, to mediate access to an application's global data, or to protect pieces of our code from being accessed by multiple threads at once, allowing it to run atomically. I'll add a link to more resources regarding POSIX threads on this video's resource page. We'll add a class property and give it an initialized value of NSLock. Then, inside of our first loop, we'll call our method on our NSLock object that tells our application to effectively lock access to one thread at a time. Now, if we run this code right away, we'll find that our application gets deadlocked, as we'd be running our lock method without ever unlocking it. When we lock our thread, we are effectively telling our program that no other thread is allowed to access this code until our current thread finishes execution of our code and hits the call to unlock. Since we never unlock, we never grant access to the next thread to run, and this is what's described as a deadlock. So we need to add an unlock function after the code we're trying to isolate, which, in this case, is just before the end of the loop. I should add that it's important to call unlock on the same thread in which we called lock in order for this to work. When using locks, we're actually forcing threads to wait in line to run, which can ultimately result in longer execution times. So, we want to lock only the crucial points of our data. Now, what we've locked here are the points where our value gets incremented. Of course, we should also lock and unlock the points where our value gets decremented as well. Now that we have our locks in place, we can build and run our application. This time, our program runs as expected, incrementing to 5,000 and decrementing back to 0. To visualize how this works, let's compare the clip we saw in the last video to how our code is working here. Previously, as our threads ran concurrently, they would fight for their turn to access our value. With locking in place, we now force the other threads to wait their turn before entering our for loops, which stops them from disrupting our sequence of operation. Of course, this has been a very simple example designed to illustrate how threads can disrupt one another if used improperly. In this video, we have seen how introducing locks can protect our global data from being mutated from other threads. In the next video, we'll look at asynchronous methods and how we can use completion handlers to force our code to wait to execute. In the previous video, we looked at how NSLock can resolve race conditions while threading. In this video, we're going to take a look at asynchronous methods and how we can utilize closures as completion handlers to wait for operations to complete to perform tasks. When dealing with concurrent programming, we need to know how to utilize asynchronous methods as the needs arise. Asynchronous methods differ from traditional synchronous methods in that once they have completed their own computations, they don't simply return a value using a traditional return statement. Instead, they utilize a completion handler, which is simply a closure that gets passed in as a parameter. The completion handler allows us to defer the execution of an operation until the necessary operation is ready. At the end of the last section, we added Alamo Fire and SW Reveal View Controller to the Game of Life application. We're going to utilize Alamo Fire to call out to a server to send and receive messages. In doing so, we'll uncover some common concurrency issues that we'll address by utilizing asynchronous methods. Bear in mind that this course is about the Swift language and not about iOS development. I've gone ahead and made some necessary changes to the application to make the focus of this exercise more clear. Feel free to download the starter project files for this video at this video's resource page. In our main game application, we've implemented a simple counter. It counts the number of iterations in each round, as well as the number of cells remaining. Once the game is complete, or is determined to be complete by our application, our program will post our scores to the server. Then we'll use a table view to display our downloaded scores. So if we open up our project and build and run it, we see the game board that we built earlier in this course with a few additions. If we tap on our game board, we are immediately greeted with an alert that asks if we'd like to post our score to the scoreboard. This isn't right. Clearly, the alert should be waiting for our game to complete before asking if we'd like to post our scores. To address this, let's review the code that initialized our game so that we can isolate the problem. If we look at our viewDidLoad in our view controller, we added a UI tap gesture recognizer that calls the method named startTimer that starts our NSTimer. Our NSTimer in turn calls a method named moment that gets called repeatedly, and each iteration progresses the evolution of our game. In our moment function, we see a call to life.evolve, and then immediately afterwards, a call to a method named endGame. Clearly, we don't want to end our game until life.evolve has reached a point of completion. So let's add a completion handler to our evolve method in our life class. We'll pass a function type which we'll name completion. This function will take an int representing the remaining cells and pass it back to our view controller. Next, we'll add some simple logic that will determine the end of the game. Since our game rarely sees numbers below 25, I'll just choose an arbitrary stopping point of about 10% of our cells. Of course, you can feel free to do whatever you like here. So, if livecells.count drops below 40, we'll trigger the end of our game and pass back our final score. Back in our view controller, let's modify our call to life.evolve to conform to our evolve's new method signature. We'll use trailing closure syntax and the word remaining as our values label. And our closure returns void. Now that our method call is valid, we'll simply move our call to endGame into our closure and pass our remaining value into it. Of course, we'll need to add self to our call to endGame since it's inside of a closure. And again, since we're referencing self inside of a closure, let's include weak self in to avoid potential strong reference cycles. Now, if we build our application and run our game, we see that the game waits until we get below the 40-cell remaining threshold before firing our call to end game. Once the pop-up appears, we have the ability to post our usernames and scores to the leaderboard. In this video, we have implemented a completion handler solution for a common programming problem. In the next video, we'll look at how we can manage concurrency with NSOperation queue. In the previous video, we looked at how we can utilize completion handlers to resolve a common asynchronous programming problem. In this video, we'll learn how NSOperation queue abstracts away the complexities of manual threading. We'll see how adding the right code to the background thread and foreground thread can improve the user experience. In most cases, our application will need to do more than one thing at a time. One of those things is responding to the user's input and making sure that the user interface is responsive. Users have little patience for an interface that appears to be frozen. There are a few ways of ensuring that your interface always remains responsive to the user. We're going to discuss an approach utilizing operation queues. We create operation queues using the NSOperation queue class, which is designed to manage our queues of operations. These operations are much like closures that contain code to perform chunks of work. Now, operation queues are not the same thing as threads. The operation queue system manages a pool of threads and allocates what it needs whenever work is being done. By utilizing operation queues instead of threading manually with NSThread, we abstract away some of the complexities around threading, like locking and unlocking threads, for instance. Furthermore, operation queues have an awareness of the computing resources available to them, which allows them to balance the operations across as many CPU cores as is available to it. Let's open up our Game of Life application and uncover a use case for an operation queue. In the previous video, we resolved an issue in our code using asynchronous programming. We have another issue to resolve with our call to get scores from the server. If you build and run your application, you'll see a menu button. Tap it to review the menu options. The menu offers different views into the leaderboards. If you click the Most Iterations menu item, an application will quickly reach out to the server and attain the latest scores, assemble the score objects, and then display them for us. Let's give it a try. All right, this took a little while because we just loaded 50,000 records, which, needless to say, we probably wouldn't do in a real application, right? Other than a lengthy loading time, you may not have noticed that the menu button was completely frozen while the application was downloading and assembling objects to our data. Let's give it another run, but this time, try tapping the menu button while the application is working. It's completely frozen. That is, until our application is finished crunching our dataset. Then it slides open at its earliest opportunity. This is happening because we've blocked the main thread. We should be doing this type of operation on a background queue. This is an easy fix with operation queues. Let's open up the highscore table view controller.swift file. If we look at our view.did.load, we have a method called getScores. Let's scroll up to getScores and see what we've got. Here, we see an asynchronous method call to an instance of a class called connect. We can see that our trailing closure does some processing on a result set. This happens to be a pretty resource-consuming operation when you consider it's operating over 50,000 records. But remember how closures work. This closure is invoked elsewhere, so there may be some more code to evaluate. Let's open up our connect class. In our connect class, we see a function named getAllScores that has a completion handler. This is our culprit. If we look inside AlamoFire's completion handler, we see that we're doing a small print operation as well as calling our completion handler. This code, along with the code in our completion closure, is currently being called on the main queue. Let's go ahead and move it to a background queue. Define a constant named background queue and give it a value of NSOperation queue. This operation queue will automatically be added as a background queue. Next, we'll wrap the code we want to be on the background queue using a method from our instance called addOperation with block. It's important to note that in Objective-C, closures are known as blocks. You'll encounter the term block from time to time in the Cocoa framework, and when you do,
Just remember that it's interchangeable with the word closure. Now that we have our code wrapped in a background queue, let's build and run our application and see how this works. I'll open my menu and load the Most Iterations tab, and then I'll try navigating. And it works. Well, sort of. Now our menu works, but our results never display. Why do you think that is? This happened because we're setting our score on the background thread, and in order to update our interface, we need to be on the main thread. This is an easy enough fix. Up in our property observer for our scores variable, we see our call to tableview.reloadData. We can wrap this call in a main queue operation queue in the same way we did for our background queue. So let's define a constant. We'll name it main_queue and set its value to nsOperationQueue.mainQueue. And just as before, we'll wrap the code that we want on our main queue. That should do it. Let's build and run and test our table view controller one more time. Navigate to the Most Iterations option, and we see our menu is responsive, and our data appears as we'd expect it to. In this video, we have seen how we can improve the user experience by properly utilizing operation queues. In the next video, we'll look under the hood of NSOperationQ and investigate Grand Central Dispatch. In the previous video, we learned how to improve the user experience by implementing background and main queues. In this video, we'll introduce Grand Central Dispatch, the low-level API that NSOperationQ uses under the hood. We'll learn why some developers choose Grand Central Dispatch over NSOperationQ, and we'll replace our operation queues with dispatch async calls. Under the hood of NSOperationQ lives Grand Central Dispatch, one of the lowest level APIs that you may ever work with as an Apple developer. Grand Central Dispatch, or GCD, is such a low-level API that it's essentially baked into the operating system kernel. What this should mean to you is that it's extremely efficient and requires very little code to use. GCD is like NSOperationQ in that it allows you to specify tasks to be performed as blocks and schedules them to be processed. Moreover, these queues are dispatched as serial queues, which means that GCD manages locking and unlocking for you, which eliminates the possibility of unintended cross-thread mutation of datasets. If Grand Central Dispatch is so efficient, why would one even bother with NSOperationQ? There are a few schools of thought on this, and I encourage you to follow this link to an excellent discussion on the topic. Essentially, NSOperationQ provides a high-level abstraction that offers some convenient features that GCD alone doesn't. The trade-off, however, is that NSOperationQ is a Cocoa object that requires a non-trivial amount of overhead to use, as it must be allocated and deallocated. If you're working with just a few instances of NSOperationQ and top performance isn't an issue, it might be the appropriate choice. However, if you're dispatching many blocks to queues, then you probably don't want to be allocating and deallocating over and over again, and in that scenario, GCD is the right choice. At the end of the day, top professionals use either one, so the choice is entirely up to you. Having said that, let's go ahead and replace our NSOperation queues in our Game of Life app with GCD. Once your project is loaded, open up HighScore Table View Controller, and let's remove the NSOperationQ queue from our property observer. We'll replace it with a call to dispatch async. Dispatch async is a C API call that allows us to interface with GCD. You'll use dispatch async in about 90% of your GCD work. What dispatch async does is it appends our specified task in the form of a closure onto a queue and then returns immediately. Notice that dispatch async takes two parameters, a queue and a block. Since this is the code that updates the user interface, we're going to make sure it's done on the main queue. We specify the main queue by passing in a function named dispatch_get_main_queue as the first parameter. Then our second parameter is a closure that contains our code. Simple enough. Let's build and run to make sure everything works. We'll navigate to our Most Iterations tab and wait for it to load. And as expected, our interface is properly updated. Now let's go ahead and replace the other operation queue that's in connect.swift with GCD. Start by removing the code that we implemented earlier and replacing it with another dispatch async call. This time, we want to get the background queue, so we'll pass in a parameter to dispatch async of dispatch get global queue with 00 as its parameters. And we'll wrap the closure around the code we want to run in the background. We'll discuss this dispatch get global queue function in more depth in the next video, but for now, let's test our application. Build and run. Once our simulator loads, navigate to the most iterations page and test the UI for responsiveness. In this video, we've replaced our operation queues with more efficient GCD dispatch queues. In the next video, we'll take a closer look at Grand Central Dispatch's dispatch queues. In the previous video, we introduced GCD and switched our operation queues for GCD dispatch async calls. In this video, we're going to look at the different dispatch queue types available to us with GCD. A dispatch queue is a structure that manages the tasks that we pass into our dispatch async or dispatch sync closure. GCD provides a few types of queues for us out of the box. However, there are others that we can use for specific purposes. There's 3 types of queues we get out of the box: serial, concurrent, and main dispatch queues. Serial queue, as the name implies, is a queue that executes one task at a time in the order in which the tasks were added to the queue. Concurrent queues, or global dispatch queues, can execute multiple tasks concurrently. The main dispatch queue executes tasks on the program's main thread and works with the main run loop to ensure that the user interface is always responsive. There are also several system-provided queues, which are linked with their own quality of service class. The QoS class essentially represents user awareness levels to help categorize how GCD should prioritize our tasks for the best user experience. The QoS class user interactive class tells GCD that the task should be done immediately. This class should be used to provide a responsive user interface. The QoS class user initiated class represents the type of tasks that are initiated from the user interface and should be performed asynchronously. This class should be used for tasks that are required in order for the user interaction to continue smoothly. The QoS class utility class is for long-running processes, generally used with user-visible feedback like a progress bar. This class is best used for networking or lengthy computations. Then there's the QoS class background class, which creates a background queue for the tasks that the user isn't aware of. This class should be used for tasks like prefetching data, background refreshing, and other tasks that aren't time-sensitive. To learn more about QoS classes, please visit this video's resource page. Let's take a look at a very common use case for these QoS classes. Here we have a familiar NSURL session and data task with request. This task comes with a trailing closure, as we've seen previously. This closure will run after our connection has either failed or succeeded. The code within the closure does a small operation before attempting to update the user interface. The code is not optimal, of course, because the 2 operations should be placed on different queues. Let's wrap our tasks in a dispatch async call. We'll start by creating a constant named quality of service class and give it a value of QoS class background. We'll create another constant named background queue and give it a value of dispatch get global queue, and pass in our quality of service constant, and we'll set the flag to 0. Flags are reserved for future use in GCD and should always be simply set to 0. Then we'll add our dispatch async call, where we'll pass in our background queue as the first parameter, and of course we'll pass in our code as the second parameter. This effectively puts our code on the background thread. But what about the code where we update the user interface? We can nest dispatch calls inside of each other when needed. So, we can make a new dispatch async call, and this time, we'll simply pass in our desired values directly, rather than creating constants. We'll pass in dispatch get global queue, and then use QoS class user interactive with a flag of 0. And then we'll pass in our user interface code into the second parameter. In this video, we introduced dispatch queues and quality of service classes. In the next video, we'll see how we can use GCD to postpone code execution until tasks have completed. In the previous video, we looked at the different types of dispatch queues available to us already, and how we can create our own. In this video, we'll learn about dispatch groups and see how we can utilize them to force our code to wait for tasks to complete using Grand Central Dispatch. Completion handlers aren't the only way to force your application to wait for asynchronous tasks to complete before continuing. Grand Central Dispatch also offers an approach by utilizing dispatch groups. To illustrate how this works, let's put together a simple application. Create a new Xcode project. I'll choose Single View Application and name it Dispatch Group and create it. In our View Controller file, we'll add a function named time-consuming task. This function is simply going to emulate a time-consuming task by putting our thread to sleep for 2 seconds. Since we want to emulate an asynchronous task, we don't want to put the main thread to sleep for 2 seconds. That would defeat the purpose here. Instead, we'll add this task to a background queue. Let's add a variable named background queue and give it a value of dispatch get global queue and pass in a quality of service class. Next, we'll wrap our sleep function in a dispatch async call, passing in our background queue variable as its parameter. So now, our time-consuming task just does something mysterious for 2 seconds before completing. Let's utilize some print statements to see this in action. In viewDidLoad, we'll add a print statement that prints the number 1, and then we'll call time-consuming task. And inside of our time-consuming task function, we'll add a print statement that prints the number 2, followed by another one that prints the number 3 after our sleep function call. Finally, we'll add another print statement to our viewDidLoad right after our call to time-consuming task, which prints the number 4. So obviously we're going to run into a problem. If we run our application, we'll see the numbers 1, 2, 4, and then after 2 seconds, we'll see 3 print to the console. Of course, we could use a completion handler to handle this issue, but we can also use Grand Central Dispatch. When using dispatch groups in this manner, you should be using them on your own custom queue rather than on the main queue. This is because, unlike completion handlers, our dispatch group halts the thread in order to stall execution while a task completes, and stopping the main thread is always a poor choice. So let's create a new queue. At the class level, I'll create a variable called myQueue that holds a value of dispatch queue create, which, as you might have guessed, creates a new dispatch queue. Our first parameter is our label. This label can be anything that we want. We just want to make sure that it's a unique name so that we can identify our dispatch queue while debugging crashes or while analyzing our application in instruments. The next parameter represents an attribute we can set to choose either a concurrent or a serial dispatch queue. For our needs, we'll use dispatch queue concurrent. Next, we'll create a new dispatch group. We'll add another variable named myGroup that simply holds a call to dispatch group create. I should note that for more complex situations, you can utilize multiple dispatch groups for managing different groups of tasks. Now that we have a new queue and group, we'll put them to work. In viewDidLoad, we'll wrap both our print statements and our time-consuming task in a dispatch async call. We'll use our new dispatch queue as the first parameter. And of course, we'll need to add self to our time-consuming task since we're inside of a closure. Right after time-consuming task, and right before our fourth print statement, we'll add a call to dispatch group wait. The first parameter takes a dispatch group, and the second parameter takes an amount of time to wait. In this case, I'll use dispatch time forever, which will force our code to wait indefinitely while our time-consuming task finishes. If we run our application now, we'll see that our application runs exactly the same. This is because we haven't explicitly stated that our dispatch group has begun doing any work. What we need to do is tell Grand Central Dispatch when our group has entered the block. We do this by adding dispatch group enter at the start of our task and passing in our myGroup variable. Of course, if we ran our application now, our program would freeze forever since we haven't indicated anywhere that our task is finished. So, much like calling a completion handler, we need to explicitly state that our task has completed. We do this by using dispatch group leave with our group as its only parameter. This time, when we run our application, we should see our numbers print out in the proper sequence. And we do. Blocking threads is a bit dirty. Fortunately, there's another approach. We can utilize dispatch group notify instead of dispatch group wait. Dispatch group notify is designed to execute after our call to dispatch group leave. We can remove our call to dispatch group wait and replace it with a call to dispatch group notify. This function takes our dispatch group as its first parameter and a dispatch queue as its second parameter. We can simply use dispatch get main queue here and wrap the code that we want to execute after our task has completed inside of its closure. If you build and run, you'll see your numbers print in proper sequence, this time without blocking a thread. In this video, we looked at another way to force our application to wait by using Grand Central Dispatch. In this section, we looked at how we can do concurrent work in our applications by using asynchronous methods. We learned how we send concurrent tasks to be processed on different threads by using NSThread. We also learned about NSOperationQ, which mitigates much of the potential downside to manual threading. And finally, we learned about Grand Central Dispatch, which is a low-level API which is utilized behind the scenes of NSOperationQ. In the next section, we're going to take a close look at troubleshooting, debugging, and error handling. Hello, welcome to Troubleshooting, Advanced Debugging, and Error Handling. In the previous section, we explored concurrency and asynchronous programming. In this section, we're going to learn about the LLDB debugger, enhancing breakpoints with conditions and actions, the LLDB command language, address sanitization, assertions, and also error handling. Now we'll move on to the first video of this section that introduces the LLDB debugger. In this video, we're going to take a look at breakpoints in the breakpoint navigator, the variable pane, and the LLDB prompt window. It's been said that about 50% of a developer's time while building an application is spent debugging it. If you've ever built an application, then you know this is pretty much an accurate statement. Whether you plan to work for an employer or for yourself, efficiency is important. If half of your time is spent debugging, you'd better become familiar with all of the tools available to you to aid in your debugging efforts. One of the first debugging tools that we become familiar with is to simply log values at different parts of our application to Xcode's console window. This simple technique can yield a lot of information about the state of the running application, which can be helpful in troubleshooting issues in our code. Of course, there's limitations to debugging exclusively with print or nslog. So let's become familiar with the LLDB debugger. Let's open our Game of Life application and open up the life.swift class. Once there, let's go ahead and add a breakpoint in our code inside of our evolve method. Breakpoints allow us to set places in our code where we want the control of our program's execution to be turned over to the LLDB debugger. After the debugger is taken over, we can view the variables in scope, examine the processes on each active thread, and even enter debugger commands that allow us to examine and even modify the state of our application. If we build and run our application, it should immediately break on the line that we specified. A few things happen when our application hits a breakpoint. Our debug navigator is presented on the left, which shows which thread our application stopped on. We can then view the different processes on each thread by selecting a given item in the thread's hierarchy. We also see that the LLDB console has opened up at the bottom in split view. The variable pane on the left has populated with all of the variables that are currently in scope. On the right, we see the LLDB prompt window, which allows us to enter commands for LLDB to run. In the left pane, we notice the letter A and the letter L next to our variable names. The letter A represents variables passed into a function as an argument, while the letter L represents a local variable. To the left of each variable, we see a disclosure triangle that allows us to expand the node to see the child variables within. For example, we've broken on a filter function that filters out our cells array, looking for cells with the current state of living. If we expand our self node, we'll see our cells variables within. Notice that it has 400 values inside of it. If we expand our cells node, we can examine each and every array item within. We can expand any one of the given elements in the array to see both the cell X chord, Y chord, and the cell's current state. Once our program has hit a breakpoint,
we can step through our application line by line by using the LLDB transport ribbon. Starting from the left, the transport ribbon allows us to continue program execution, which tells our program to continue execution until another breakpoint is hit. Since we've broken on filter, which we know to be a loop under the hood, clicking continue will step us through each item in the array. Next is the step over button, which tells the application to jump to the next line of code. This button stops the debugger from following deep into methods that may not be helpful to debugging our current issue, such as framework-level code or even assembly code. Then there's the Step Into button, which tells our application that you do actually want to step into each method to explore every line of that function and each subsequent function involved in our program's execution. Of course, if the next step is not a function, our application just jumps to the next line. Finally, there's the Step Out button, which is helpful after you've stepped into your application a few times and you begin stepping into code that's not relevant to your problem anymore. Clicking Step Out allows us to jump back out into the place in our code where we initially set our breakpoint. On the right side of the LLDB ribbon, we can view the hierarchy of our code. More specifically, it shows us which thread we are currently paused in. Right now, it shows that we've paused execution in our life class on a function named evolve, which is running on thread 1. If we click on the execution hierarchy, we see a stack view that displays all of the code resulting from the method where we placed our current breakpoint. Notice that the method we broke on is numbered with a 0 in the call stack. If we click on number 1, we'll be taken to the previous method in our application, meaning the method that actually called our evolve method. We can click on each item all the way up the stack back to the beginning of our application's lifecycle. In this video, we introduced the LLDB debugger. In the next video, we're going to dig deeper into breakpoints and make them more effective for debugging. In the previous video, we looked at the LLDB debugger in Xcode. In this video, we're going to see how we can get the most out of our breakpoints. We'll look at a few different types of breakpoints, as well as how to run actions when our breakpoints are hit. The first type of breakpoint that we're going to look at are called conditional breakpoints. Conditional breakpoints allow us to tell Xcode that we only want to pass our session to the debugger if a value reaches a specific condition. To demonstrate this, we'll just use a simple for-in loop and we'll set a given condition. Let's create a new single-view application and name it breakpoints. Once our application is loaded, we'll add a function named breakpointTest. And we'll paste in a simple loop that loops through the range of our values. Place a breakpoint on the breakpointTest function inside of the for-in loop. Next, click on the Breakpoint Navigator in the Project Navigator ribbon. Now, we can edit our breakpoint by right-clicking on our breakpoint and choosing Edit Breakpoint. Notice the condition box here at the top. You can enter any condition that results in a Boolean true or false here. In this example, we'll just write val equals 200, so this breakpoint should only fire when our value is equal to 200. Build and run, and let's see if it fires as expected. Our application breaks, and we see in our console window 200 print statements. Let's stop our application and edit our breakpoint again. This time, let's stop it at 2000 and see if our application breaks. This time, our application continues to execute as expected. One thing that you may have noticed while running our application with this conditional breakpoint is that it runs very slowly. It takes over 5 seconds to iterate over 2,000 values. This is because Xcode turns our application over to the debugger every single time it evaluates. Another thing that we can do with breakpoints is to define an action to be carried out when our condition is met. Let's right-click on our breakpoint and select Edit Breakpoint. We'll change our condition to val greater than 900. Next, click the Add Action button. This reveals an input box which allows us to enter debugger commands, which we'll cover in a later video. For now, we'll just add the following LLDB command, printVal, which will print out each value that meets our condition. Before we run, check the Automatically Continue After Evaluation Actions checkbox. Build and run the application,
and we'll see our values slowly iterating through our range as expected. Once we pass 900, we start seeing additional print commands firing in the LLDB output window. Another type of breakpoint we have at our disposal is the symbolic breakpoint, which allows our breakpoint to be triggered every time a given function is called. The function does not need to be in our own source code either. We can also break on system and third-party framework code. Before we get started, let's add a function to our program named SumFunction that has a simple print statement in it. Then we'll update our loop with a condition. If our value is equal to 950, then we'll fire our SumFunction method. Setting up a symbolic breakpoint is a bit different than setting up regular breakpoints. Rather than setting our breakpoint in our editor, we'll click the Breakpoint Navigator button in Xcode's Project Navigator ribbon. Then, click on the plus icon in the bottom left of the pane. Find Add Symbolic Breakpoint from the dialog and select it. You'll see a blank breakpoint appears along with the dialog. The first input box allows us to specify a symbol. We'll add viewController.SumFunction to specify our new function. Of course, we've got access to conditions, actions, and we can even specify a module for our scope. For this example, we'll just use a symbol. Now that we have our symbol, let's build and run our application. And we see our breakpoint triggers right when our loop hits 950, and our SumFunction method fires. Let's look at one more type of breakpoint, which is the exception breakpoint. Exception breakpoints can be tremendously useful when troubleshooting the source of an exception. We're going to update our code one more time by throwing an exception in our SumFunction method. We'll start by modifying our method definition to include the throws keyword, which tells our calling code that this method has the ability to throw exceptions. We'll raise a simple generic NSException and add the following statement. NSException with parameters name set to myCustomException, reason, breakpoint, set userinfo to nil, and then call raise to raise the exception. Finally, in our for-in loop, we'll add a do-try-catch statement that attempts to run our SumFunction, which, as we know, will throw an exception. We'll be taking a closer look at this type of error handling in an upcoming video, but for now, this should do the trick. Let's remove the existing breakpoint, and then we'll build and run. We see that we're taken to the app delegate, and our exception is thrown. This isn't terribly useful. It would be nice if Xcode would actually show the code that threw the exception. That's where exception breakpoints come in. Let's go to the Breakpoint Navigator and add a breakpoint. Select Exception Breakpoint, and we'll leave the defaults as is. Build and run, and you'll see that we're taken right to the source of our exception. However, we don't see an actual exception in our LLDB prompt. We can fix this by editing our breakpoint to utilize an action. In the Breakpoint Navigator, right-click on the exception breakpoint and select Edit Breakpoint. When the dialog appears, click the Action button and add the following LLDB command, PO, and then inside of square brackets, $arg1 name. This retrieves the name of the thrown exception. If we build and run our application, we see that our application breaks at the exception's origin and prints out the name of the exception. I haven't covered all of the different breakpoints here. We also have access to Swift error breakpoints, OpenGLS error breakpoints, and test failure breakpoints. You can visit this video's resource page for more information on breakpoints. In this video, we have seen multiple ways to enhance our breakpoints. In the next video, we'll introduce the LLDB command language. In the previous video, we looked at several ways to improve the usefulness of our breakpoints. In this video, we're going to take our LLDB debugging skills to the next level by learning some LLDB commands, which will allow you to print values, navigate breakpoints, and even manipulate session variables. Believe it or not, everything that we've done already, from creating breakpoints to applying conditions and actions, can be done by using LLDB commands in the prompt window on the right. In this video, we'll go over some useful commands and see where we can discover more. Let's open our project and remove any existing breakpoints. We'll add a simple breakpoint that'll fire when our application hits our val variable inside of our for-in loop. So build and run, and we'll immediately hit our breakpoint, and our session will attach to the debugger which gives us access to the LLDB prompt window. The first command to try is the help command, which gives us a list of all of the commands available to us. This is helpful, of course, for learning new commands, or for when we need a reminder of what a particular command does. As we scroll through the list, we see the same navigation commands that are available to us in the LLDB ribbon. We see C and also continue, two ways of continuing from a breakpoint. Let's test some of the flow of control commands that help us navigate through our debugging session. First, we'll test continue, or C for short. If we enter C into the LLDB prompt and hit enter, our loop cycles once and breaks on the next iteration. Let's try step over next, which is also alias to next or just N for short. Type N in the prompt. We can repeat this a few times and we'll step through our loop. We also have a step in command, which allows us to step into functions like before, and the step out command, which allows us to step out by advancing our application to the nearest return call. We can also print variables that are in scope with the print command. We can print out the current value of our val variable by typing pval and pressing enter, and we see our current value printed to the console. We can actually print out anything in our class. Stop the debugger and let's create a dictionary at the class level with some arbitrary data. Let's name it myObject and just give it some arbitrary values. Build and run the application again, and when the program breaks, enter print_self.myObject into the LLDB prompt and hit enter. We'll see our object printed out just as LLDB sees it. It's important to note that any value we see with a $sign in front of it can be printed like a variable. For instance, if we print out this $R value from here, we'll get the exact value printed out. We can also print functions. For instance, entering print_self.breakpoint_test prints out our function's type signature, takes void and returns void. And we can even print self to see the contents of our current instance. You can modify values on the fly by utilizing expressions. We can set our val variable to whatever integer we like by typing expression val equals 99, for instance. Then we can print out our variable to see the newly assigned value. We can even add two variables together to create a value, like this. Expression val equals 99 times $R2. Printing this will show the product of our assignment. Now, this is just an introduction to the LLDB commands. There are too many commands and use cases for commands to cover them all here, but I encourage you to check out this video's resource page where I'll share some additional examples of LLDB commands as well as some excellent resources. In this video, we have introduced the topic of LLDB commands and improved our debugging skills. In the next video, we're going to take a look at address sanitization while working with Objective-C or C. In the previous video, we looked at how to use the LLDB command language for debugging. In this video, we're going to take a look at Xcode's address sanitizer that works with Clang-based languages for detecting deeper memory problems. The address sanitizer is a feature for languages using the Clang compiler that allows you to better find memory issues such as buffer overflows, use after free errors, double free, and other memory corruption bugs at runtime. This is helpful for when interoperating with languages like Objective-C or C. Since Address Sanitizer doesn't work with Swift alone, we'll need to put our interoperability knowledge to work to create a memory problem. Let's open up our previous project and we'll add a new file to our project's root folder. Select iOS, then C file, click Next, give it a name, and save. I'll paste in the simplest function that will result in a buffer overflow for the address sanitizer to pick up on. Next, we'll create a header file with the same name. Select iOS and choose Header File. Click Next, name it, and create. This file will just reference our buffer function. Finally, we'll add a bridging header file. Select iOS and then choose Header. Click Next, name it the same name chosen for the application, then dash, bridging, dash, header. If you need a refresher on bridging headers, revisit Section 4, Interoperability and Working with Third-Party Libraries. Next, click on the root application and select Build Settings. Then scroll down until you see Objective-C Bridging Header. Click the blank field and a pop-up appears. Then drag the bridging header from the Project Navigator into the dialog and you'll get a file path, and then just delete all of this text. We'll create a memory problem in our sum function method by calling our buffer function. If we run the application, we get an error that takes us to the app delegate, but that's the extent of the detail that we get. Let's enable address sanitization by clicking Edit Scheme, then Diagnostics, and then by clicking Enable Address Sanitizer. Xcode will know to rebuild the application with address sanitization, allowing us to capture more details at runtime. If we build and run our application again, we'll see a much different error. This time, we are taken to our C code and shown right where our error lies. We're also given an extensive stack trace revealing quite a bit of details. We get even more details in our debug navigator. We can see that our memory issue occurred 15 bytes after a 2-byte heap region at this location. We can click any of these events and walk through the thread's process frame by frame to learn more about the problem. We can get a more granular view of our memory by clicking on the address here to see which portions of our memory are valid or invalid. This is our memory view. Everything that we see here that's grayed out is invalid, while everything that is not grayed out is valid memory. Again, this can be a very handy feature when interoperating with C or Objective-C. To learn more about address sanitization, please visit this video's resource page. Address sanitization is a pretty cool feature. We saw how enabling it can improve the error message while interoperating with Objective-C or C. In our next video, we'll look at another useful debugging technique by using assertions. In the previous video, we looked at how Xcode's address sanitizer can reveal details about Clang-based memory issues. In this video, we're going to look at different types of assertions, and particularly the assert method. In some situations, it is simply not possible for our application to continue functioning if a particular condition is not satisfied. Assertions are a handy debugging tool that allow us to make sure that our essential conditions are satisfied before continuing execution. If our asserted condition evaluates to true, our application runs as expected. Otherwise, our application is terminated. Assert is only evaluated in debug mode. So if an assertion is put into production, it will never be evaluated. We'll make sure to demonstrate this later. Let's start by creating a new Xcode project. We'll name it Error Handling and click Create. We'll open up our viewcontroller.swift file and write a simple assertion in our viewDidLoad to see how it acts. We'll start with the keyword assert and pass in a Boolean for our condition, along with a useful error message to be displayed. If we build and run our application, we'll get an assertion failed message in our LLDB console. And we see assertion failed, the condition was false. Now let's use assert in a more realistic manner. Asserts are really helpful when building portions of our applications where we may be uncertain whether valid data is being passed in or not. Let's create a new function that takes an array of integers. This function will take the input array and run a reduce function that sums all the values before returning. Build and run the application, and we see it runs without a problem. What if this data was crucial to the user's experience, but not to the overall functionality of the application? This solution, however simplistic, demonstrates a common use case for an assert. Let's now modify our function to employ an assertion. We'll once again call the global assert function that must be met in order for our application to operate as expected. We'll pass in an error message to be displayed to the developer. Let's build and run our application again, and this time we get an assertion failed. This is precisely what we want. As mentioned previously, assertions are only evaluated in debug mode. To demonstrate this, click on the root application followed by Build Settings. Under the Swift compiler section, simply switch the debug value to fast and rerun the application. As expected, our assertion never fires. The Swift standard library offers 4 more global assertion functions that differ from each other in how they affect the flow of our code. We just saw assert, which is a C-style assert that allows us to do sanity checks while actively developing and testing. Next is assertion failure, which we can use to indicate that a check has failed or to halt execution when control flow reaches undesired code. Precondition is much like assert in that it checks a necessary condition before making forward progress in the app. More on this in a moment. Precondition failure indicates that a precondition was not satisfied by terminating execution. And fatal error, which unconditionally stops execution and prints a message to the console. You may have noticed that precondition is much like assert. One big difference, however, is that assert is designed for sanity checks during development or testing, while precondition is for guarding against things that, if they occur during the application's lifecycle, would mean that the program can no longer proceed as expected. Another big difference between assert and precondition is that precondition will get evaluated in production. Of course, I'll have some more information about these different assertions on this video's resource page. In this video, we have seen how we can assert conditions to be true, causing catastrophic failure if the condition is false. In the next video, we'll look at error handling in depth. In the previous video, we looked at how we can use assertions to manage edge cases in our code. In this video, we're going to demonstrate how to utilize try, catch, and throws to gracefully handle errors when they occur. We'll also see some custom error types and functions that can throw. As of Swift 2, Swift offers first-class support for throwing, catching, propagating, and manipulating recoverable errors at runtime. When an error is thrown, we'll generally want to handle our error by injecting a default dependency or by using a secondary approach to the task at hand. When a method throws an error, it changes the flow of the application, so it's important to recognize places where your application can fail and create strategies to prevent it from crashing. Let's set up some basic error handling around a function that gathers data from a local plist. With the error handling application opened, we're going to create a simple function named dict from plist, which will attempt to read from a non-existent plist file and return a dictionary. Since the Swift compiler doesn't know if we're going to find a value or not, our call to path for resource returns an optional. So if we wanted to, we could simply change our method signature to return an optional and then force unwrap our value. Then we'll call dict from plist from our viewDidLoad. We can go ahead and add a traditional if-let statement to unwrap the result. Let's build and run and see how this fares. Of course, our application crashes with a fatal error since we don't actually have a plist to read from. This is an example where the reason for failure actually matters. Maybe we've used the wrong file extension. Maybe we don't have privileges to access the file, or perhaps, as with the current case, the file doesn't exist at all. For brevity, we're going to write an enum with just one case. We'll name our enum file path error and make it conform to error type, which makes it throwable. We'll define just one case for bad file path, but we could conceivably create cases for both access denied or bad file format as well. Now, we'll need to modify our function to allow for throwing. We'll do this by adding the throws keyword, and we'll remove the optional return type. Once that change is made, we'll see our call to dict from plist has an error. Any function in Swift that can throw must be wrapped in a do scope and a try-catch statement. So we'll just comment out our if-let statement and add a do statement. Recall that do creates a working scope for us. Above our do scope, we'll add an uninitialized variable named dict that is a placeholder for our dictionary. Within our do scope, we'll set our dict value equal to our dict from plist function. This presents us with an error that says call can throw but is not marked with try. As the message states, any function that can throw must be preceded with the keyword try. So we'll add that and quiet the compiler. The last thing that we need is a catch statement. We'll add a generic catch statement for now with a print statement inside. If we ran our application as is, it would simply crash in the same place as before when it tries to unwrap the file path variable. In order to take advantage of our try-catch, we'll need to evaluate the file path variable and throw an error. We can do this by simply modifying our file path declaration into a guard statement to see if the file path is nil. If it is nil, we'll throw filepath_error.badFilePath. If we build and run the application, we'll see that our application doesn't crash this time, although our catch statement has reported an error. In our try-catch statement, we're just watching for any type of errors, but we can create different catch statements for different error types. Let's modify our catch statement to handle both generic errors and our bad file path error by inserting another catch above our existing one, and then by adding the name of our enum followed by the case we want to handle. Then we can rewrite our catch-all statement to be more suitable to its purpose. If we run this, we see file path error bad file path, which doesn't really tell us much. What if we wanted to get more information out of this error? We can do this by associating a type with our enum's bad file path case. Let's update our bad file path by adding a parameter that takes a string named message. We'll then need to update our throw statement by adding a message. We'll just add a descriptive message here. And finally, let's update our catch statement to handle our new associative enum case. That should do it. Build and run, and you should see your error message printed to the console. There's quite a bit more to be said about error handling. For more discussion and some links to external resources, please view this video's resource page. In this section, we introduced the LLDB debugger and command language. We looked at how we can modify breakpoints to better suit our debugging efforts. We saw how to use address sanitizer to reveal bugs in Clang, and we also discussed assertions and error handling. In the next section, we're going to get a grasp on Big O notation and the performance implications behind our programming choices. We'll also look at some ways to improve performance through both compiler optimizations and by implementing more efficient algorithms. Welcome to Section 7, Performance Optimization and Intro to Algorithms. In the previous section, we looked at advanced debugging and error handling techniques. In this section, we're going to investigate several different performance optimizations that you can apply to your applications. We'll look at how you can take advantage of compiler optimizations. We'll see how you can measure performance. We'll see some programming tips that can yield immediate results, and then we'll end this section by building an awareness of algorithms. Now we move on to the first video of this section that deals with identifying performance bottlenecks with XCTest and Time Profiler. In this video, we'll learn how to analyze our application's performance and identify expensive operations with Time Profiler. We'll then learn how to measure the performance of our code using XCTest. Understanding the performance implications behind our coding decisions is a very important step to becoming a good programmer. In this video, we're going to investigate two different approaches for measuring the performance of our code. The first approach allows us to take a high-level look at our application using Instrument's Time Profiler. Like the allocations tool we used to profile memory issues in Section 3, Time Profiler allows us to attach and record a debugging session which helps us to gain insight into the resource-heavy portions of our code. After we spot a performance bottleneck, we can then inspect the issue more closely to isolate the problem. The second approach is often useful after isolating a problem with Time Profiler. XCTest allows us to take a closer look at the speed of our operations. This allows us to quickly A/B test our code and see which choice is better for performance. Let's begin by opening our Game of Life application in Xcode. If you've lost track of your copy, you can always download the starter files for this video here. Once your application is loaded, go ahead and build and run it. We'll then transfer our session over to Instruments. In a simulator, go ahead and navigate to the Most Iterations menu and let our object construction process compute. You can see it register here in our CPU usage lane. Let's stop our Instruments recording and take a look at this. We can filter our desired results by clicking and dragging in the lane over the captured measurements that we wish to isolate. If you have a trackpad, you can pinch to zoom in, or if you have a mouse, you can hold Option and use the wheel to zoom in and out. Hovering over the timeline will show you your CPU usage over time. Notice that this operation uses over 100% of the CPU. This is because Time Profiler sums up all concurrent activity and, if you recall in the last section, we moved some of our work onto our background thread. Notice in our call tree view that the most resource-heavy operation is on the background thread, while our main thread still has some headroom. This is exactly what we wanted. We can inspect these processes with more granularity by expanding nodes. I'll expand them until I see the actual method calls that are using the bulk of the CPU power. You can see here that appending our objects to an array is using quite a bit of CPU. Once we have found a point of interest, we can double-click on the item and Time Profiler will show us the code in question. Let's look at another view of our recorded measurement. In the top right, we have 3 switches, which are called strategies. The first one is the CPU data strategy. It shows the CPU usage by core. We can zoom in closely to view the activity on our cores. This is an excellent way to prove to yourself that our operations are indeed happening concurrently. If you see any activity overlap adjacent swim lanes, you have concurrency. The next strategy is the instrument data strategy, which gives us a high-level view of our overall CPU usage. And the last view is the thread data strategy, which gives us a detailed view of our thread usage. These blue symbols represent snapshots taken of our thread, which allows us to see the stack from that thread at each given timestamp. Let's go ahead and measure our game's performance. We'll rerun our application and transfer our session to instruments once again. Once Time Profiler has taken over, we'll run our game. So we see the bulk of our operation is on the main thread, which makes sense considering that the game board is being rendered over and over again based on our computations. Let's follow this resource-heavy node down the stack. If we follow it long enough, we find our custom filter we wrote in section 2. This might be a good opportunity to A/B test with XCTest. We can test our filter against Swift's filter to see if there's a performance difference. Let's navigate to the Game of Life's test folder and open the Game of Life test Swift file. While we can certainly use XCTest for unit testing, we can also use it to measure performance, as we'll be doing throughout this section. At the top of our test class, let's create a placeholder variable for our life class. We'll utilize the setup function to instantiate our life class before each test runs, and we'll set it to nil in our teardown function to ensure that each of our tests starts with a clean slate. Finally, we'll utilize measure block function and add the code we'd like to measure. In this test, we'll be measuring the evolve block that contains our custom filter. Before I run this test, I want to point out that we are not running our entire game. We're running our evolve loop one time on a fresh instance of our cells class. So these tests are going to be pretty fast. Now let's run our test by clicking the diamond next to our class in the gutter. And our test completes. Next, let's open our life class and change our filter implementation to Swift's. We'll go back to our test file and rerun our operation. Notice we get very similar times. But Swift's filter is slightly faster in this case. We're going to continue this discussion in the next video. In this video, we introduce 2 ways of measuring the performance of our code. In the next video, we'll look at different compiler optimization modes. In the previous video, we introduced 2 ways to measure performance. In this video, we're going to continue where we left off, but we'll shift the dialog to compiler optimizations. Compiler optimization modes change the way Xcode's LLVM compiler compiles your code. By default, it compiles each code file individually, allowing the compilation of your code to take place on multiple cores. This, of course, makes for faster build times during development. In this default mode, when you rebuild your application after making some changes, Xcode only recompiles the code that needs to be updated, making for much quicker builds. The problem is that the compiler's optimizations are limited to the scope of one file at a time. Xcode 7 introduces a new optimization mode named Whole Module Optimization, which, as the name implies, optimizes the entire module at once. This provides a tremendous performance boost as the compiler can analyze the whole module and make aggressive optimizations to the generated binaries. The trade-off, of course, is that the whole module optimization build takes longer because you're recompiling the entire module each time. For an in-depth discussion on compiler optimizations, I would recommend watching WWDC 2015 Session 409 titled Optimizing Swift Performance. I'll provide a link on this video's resource page here. Let's look at whole module optimization in action. In our last video, we were getting very similar speeds between our custom filter operation and Swift's filter operation. This is a bit odd considering that our custom filter is built quite a bit lighter than Swift's. Our filter leans on the array type rather than conforming to sequence type and rolling our own generator like Swift's filter does. Swift's filter also has the added functionality of being able to throw and rethrow errors. Let's change the mode of operation to see if it garnishes any different results. Click on the root project and select Build Settings. Once there, type Optimizations in the search field to filter our options down. We'll take our debug and switch it to whole module optimization mode. Now let's rerun our tests starting with Swift's filter type. Open life.swift and make sure we're using Swift's filter. Then open your test suite and perform the measurement. As expected, whole module optimization mode is quite a bit faster. Let's test our version of filter to see if there's been an improvement. Open life.swift and switch Swift's filter for our custom filter. Now let's go back and rerun our tests. Okay, this time we're running measurably faster. Let's run our application and see if it's noticeably faster with whole module optimization. Once your application is loaded, run your game. This is notably faster. Let's look at it side by side. The left side of the screen is with optimization, and the right side of the screen is with no optimization. Let's switch whole module optimization off and run Time Profiler on our game and see how it performs. Let's build and run, and transfer our session to Time Profiler, and then we'll run our game. Now that we have some measurements, let's see how our application performed. Before we switch to whole module optimization, let's see how much CPU our custom filter function uses. We'll have to expand a few nodes and here it is. Let's switch from no optimization to whole module optimization and build our application. Now let's transfer our session to Time Profiler and run our application again. And we see we're using a fraction of the CPU power that we were without whole module optimization. Again, let's see how our custom filter fared. This is interesting. Our custom filter function is nowhere to be seen. This is because the Swift compiler is actually inlining our Swift function, which is another reason why our custom filter runs faster than Swift's native filter in whole module optimization mode. An inline function is a function that is stored and called directly from an address, which is also known as a call instruction. Ordinary functions use this call instruction to transfer control to the function's definition. Avoiding this definition lookup can often speed up our function's call. For more information on inline functions, see this video's resource page. Let's see what happens when we tell Swift not to inline our function. Open utility.swift and add the following line above our custom filter function. This will tell the compiler never to inline this function call. Now let's build and run our application and transfer it to Time Profiler once again, and then run the game. Let's drill down the main thread stack and look to see if our custom filter function exists. And there it is. In this video, we've effectively used Time Profiler and XCTest to track down why our filter function was performing better than Swift's in whole module optimization mode. In the next video, we'll see how we can improve the performance of our code even further by reducing dynamic dispatch. Welcome to Reducing Dynamic Dispatch. In the previous video, we looked at how compiler optimization modes affect the performance of our code. In this video, we're going to take a look at dynamic dispatch. We'll discuss the performance implications behind this type of dynamism, and we'll introduce the final keyword, which can provide a drastic performance boost. As with many other programming languages, Swift allows classes to override methods and properties that are declared in its superclass. This means that the application has to determine at runtime which properties and methods are being referred to and then perform an indirect access call. This is dynamic dispatch. Dynamic dispatch is what allows Swift to be so flexible, but the trade-off for gaining this flexibility is runtime overhead for each indirect usage, and, as you know, all of our classes, methods, and properties are labeled as indirect by default. Dynamic dispatch calls are achieved by using virtual lookup tables to locate methods and then perform indirect calls. This is not only inherently slower than performing a direct call, but it also prevents compiler optimizations, which make indirect calls even more expensive. However, we're able to trade our dynamism back in for performance by utilizing the access modifiers final and private. The final keyword invokes a restriction on the class, method, or property. It tells the compiler that the object marked with final cannot be overridden and in turn allows for direct calls and compiler optimization. Let's see this in action. With our Game of Life application open, we'll navigate to the life.swift file and add the final keyword to our class definition. This marks the entire class, including all of the properties and methods, as final. Now let's navigate to our XCTest suite and run our tests. Keep in mind, we're already using our faster filter method along with whole module optimization and the final keyword. Let's run our test and see how it performs. Now, our evolve method is running at just 3/1000ths of a second. This cuts our previous best performance in half. Let's see how this change has affected our game's performance by testing it in Time Profiler. Let's first remove the final keyword and get a baseline CPU speed for a frame of reference. Now, let's run our application and transfer our session over to Time Profiler. Once your simulator is loaded, run your game and see how it performs. This is already pretty good performance, but let's see how adding the final keyword to just our life.swift class enhances our performance. Once you've made your changes, run the application and again transfer your session to Time Profiler. Once our simulator is ready, we'll run our game. And we get a rather impressive performance boost of about 10 percentage points. I'm seeing CPU usage as low as 11%. Go ahead and test the final and private keywords on more of your classes, properties, and methods to see how low you can get your CPU. In this video, we looked at how limiting dynamic dispatch can greatly improve the performance of our code. I encourage you to try these techniques in your older applications to see how much faster you can make them run. In the next video, we're going to look at the relation between reference types and performance. In the previous video, we learned how to reduce dynamic dispatch to improve our application's performance. In this video, we're going to measure the differences between reference types and value types to gain an understanding of how the two perform. In video 4 of section 1, we discussed classes, structs, and enums, and illustrated some of the differences between reference types and value types in theory. We further developed this conversation in videos 2 and 3 in our section on memory management, where we demonstrated how we can assist Arc in eliminating reference counting overhead. In this video, we'll measure the impact of reference types over value types using XCTest. The more mindful we are about the programming choices we make, the more optimized our code will be. In Xcode, create a new single-view application and make sure you include unit tests. Once your application is loaded, add a new file and name it whatever you like. In this new file, we're going to create two simplified versions of int, one as a class and one as a struct. We'll also need to overload the plus operator to handle our new types. Create a class and name it referenceTypeInt. We'll give it a single property named value, which will hold a Swift int. We'll also create a simple initializer, which will take an int. Now, for our struct, we'll simply copy our class and give it a name of valueTypeInt. Next, we'll paste in our overload for our plus operator. This is a fairly common overload of the plus operator. The way this works is that our left-hand side parameter represents the object on the left of the plus operator, while the right-hand side parameter represents the object on the right of the operator. We simply return a summed version of the object by passing the sum of the addition into our initializer. Once again, we'll copy and paste this for our value type and make the necessary changes. Okay, this is enough to run our tests. Open your test class and we'll remove everything we don't need. We'll create a test function named testReferenceTypeInt and we'll add a call to our measure block. We'll define a variable named refType and give it a value of referenceTypeInt and pass in an initial value. Then we'll create a for-in loop that iterates through a range between 1 and 1,000,000. Inside of our loop, we'll give our refType a new value by adding refType to a new instance of referenceTypeInt in which we'll pass our index. Let's go ahead and duplicate this method. We'll make the necessary changes to test our value type. And with that, we can run our test class by clicking the diamond in the gutter next to our class. The test's complete, and we see our class operation took a little over 0.2 of a second, while our value type operation took about 0.008 of a second. This is a pretty substantial difference already that illustrates the power of immutability in a Swift language. Let's set the speed as our baseline and then rerun our tests with whole module optimization turned on. I'll navigate to my project's build settings and switch it on. And then I'll head back over to my test class and run the operation again. With whole module optimization enabled, the compiler is able to further optimize our value type, giving us a 20% boost in performance, while our reference type only receives about a 5% boost. I should note that this is a really primitive test that was designed to clearly polarize the performance differences between classes and structs. With more complex structs, especially structs containing mutating functions or references to other classes, the performance gaps in our tests would be much less severe. In this video, we demonstrated the difference in performance between reference types and value types in Swift. In the next video, we'll discuss how whole module optimization can optimize the performance of generics. In the previous video, we measured the performance of reference types and value types. In this video, we'll demonstrate a compiler optimization called generic specialization. In Section 2, we saw how generics can afford us maximum code reuse. There is, however, a caveat to generics that I've yet to mention. The Swift compiler is able to optimize methods based on their types. However, with your compiler optimization set to none or even fast, the Swift compiler cannot optimize a generic method since the incoming object can be of any type. Generic specialization is a compiler optimization that is afforded to us by whole module optimization. Since whole module optimization compiles the entire module rather than a single code file, the compiler is able to infer the type and perform any necessary optimizations that the type is eligible for. Let's create a new Xcode project. Make it a single-view application with unit tests. Once your application is loaded, we'll create a new file which we'll name genspec. We'll define the two methods we wish to test. The first we'll call intMax, which will take two ints, x and y, and return one int. Our return statement says, if y is greater than x, return y, otherwise return x. Now we'll create our generic version, which we'll name genericMax. It will take a type t that conforms to comparable. Our genericMax will take two generic parameters and return an item of the same type. Other than that, our methods will be identical. It's important to note that our test suite is a different binary, so whole module optimization won't optimize our functions if they are called directly from our tests. So in order to measure our generic function properly, we need to create two wrapper functions that return the result of our custom functions. I'll create one function named generic int max, which will take two ints and return one, and then simply return the results of our generic max function. We'll do the exact same thing for our non-generic int max function. Now, we'll be able to test our operations with whole module optimization. Navigate to the test class and add a property named genSpec, which is of type generic test. Then, in the setup, we'll initialize our generic test object. We'll make sure to set our genSpec to nil in our teardown. Let's edit the name of our test to test generic performance. And then, inside the measure block closure, we'll add a for-in loop that iterates over an array from 0 to 10 million. Inside our for loop, we'll call our generic test instance and call our wrapper method, passing in two random numbers. If you'd like a more concrete test, you're welcome to use two hard-coded integers if you like. Next, we'll simply copy this test method and change the name to test non-generic performance, and switch the method that we're calling. If we run each test now, we should find that our non-generic function outperforms our generic int function. Which, as expected, is precisely what happened. So here's why. In order for our generic function to be able to handle any type, the compiler is adding some needed code to our function at runtime. With whole module optimization turned on, our compiler will use a special optimizer called generic specialization, which will help our generics to infer and optimize for the incoming type. So let's turn whole module optimization on now. We'll head over to our build settings and filter our results. We'll change the debug optimization from none to whole module optimization. Now, if we run each test, not only will we see an enhancement of overall performance, but we should also see very similar results between our generic max function and our int max function. And this is exactly what we get. Again, this is a good opportunity for you to go back through the code you've written in the past and measure the performance with whole module optimization turned on. In this video, we have seen how to improve the performance of our generic functions through generic specialization. In the next video, we'll introduce some algorithms and big O notation. In the previous video, we saw how to put generic specialization to work to improve the performance of our generic code. In this video, we'll begin our discussion on algorithms by comparing a linear search against a binary search. To be clear, the goal of this discussion is not to give you a specific tool that will solve all of your performance needs, but help to build awareness of the performance implications behind your programming choices. We can think of an algorithm as a step-by-step strategy for solving a problem. Of course, there are many ways to solve pretty much every programming problem you come across in Swift. So the question becomes, how do we determine which strategy or algorithm is the right one for the job? Big O notation is a way to classify and communicate the efficiency of software algorithms as their input size n grows. The best way to understand Big O notation is by comparing and measuring algorithms. Let's create a new Xcode project with unit tests. Once your application is loaded, add a new file named Big O and provide a class with the same name. We'll add three properties. We'll name the first property giant number and give it a value of an array of ints and initialize it to hold 100 million integers. The other two properties will serve as counters to track how many steps each algorithm takes. We'll name one linear steps and the other binary steps. We're going to use two different approaches to finding our specific number in our array. Our first approach is a linear search, which uses brute force to iterate through the array sequentially and find our value. The next approach is by using a classic binary search. A binary search allows us to apply our knowledge about the data to help reduce the criteria of our search. Since we know the lowest number we have is 1, and the highest number is 100 million, we can eliminate possibilities in an elegant manner. We'll define a function named linear, which takes an int, and then we'll add a simple for-in loop that contains a check for our value. When our linear search succeeds, we break out of our loop. Our linear function can be described as an O times n algorithm, meaning that the order of complexity increases evenly by the number of items that we're iterating over. Next, we'll define a binary search function, which is an O times logarithmic n algorithm. This means that while the input number increases, over time the complexity increases, although much less significantly. I'll go ahead and paste in the code and explain it line by line. This function takes 3 ints as arguments: a value, a start index, and an end index. Then we locate the middle index and use that index as a key into our giant number array. Then we check to see if our selected number is greater or less than the value given. If it's greater, we'll reduce our range. If it's less, then we'll increase our range. If it's not one or the other, then we have found our number. Then we'll create wrapper functions to call our algorithms from our tests. And then we'll set up our tests. At the top of the test class, we'll create an instance of our big O class. Then we'll add 2 test functions, one for our linear test and one for our binary test. Once they're wired up, we'll run our tests to see how they perform. In my test, the linear search takes about 9 seconds to perform, while our binary search takes only a few thousandths of a second. The reason why the binary search is so much faster is that it took only about 260 steps to complete, while the brute force linear approach had to step through each item to find our value. Our test perfectly illustrates the power of selecting the right algorithm for the job. Of course, the complexity of the implementation needs to be balanced with the magnitude of the task at hand. In other words, we don't need to implement a binary search algorithm to search through a 10-item list. But regardless of the task at hand, we should always bear in mind the complexity of the algorithms we choose. To see more comparisons and to find a link to an excellent repository containing popular algorithms written in Swift, visit this video's resource page. In this video, we looked at 2 different algorithms for a common problem. In the next video, we'll learn about an algorithm that caches computations. In the previous video, we introduced big O notation and began learning about algorithms. In this video, we're going to take a look at how we can improve our performance by caching computations. We'll then look at the classic memoize function and test its performance. The most common implementation of memoization was introduced in WWDC 2014, session 404 on Advanced Swift. In this video, we're going to break down the memoize function as it was introduced by Apple and measure it as we go. Memoizing is a way of improving the performance of functions that perform the same computations over and over again. We do this by introducing a caching mechanism that stores the results of the expensive computation. With the results of our computation stored, we can then simply return the cached value of the computation based on the input rather than reperforming the operation. We'll start with a simple non-generic memoize function. Then we'll introduce and deconstruct a generic version. Create a new Xcode project with unit tests. Once done, add a new Swift file and name it memo. We'll add a class with the same name and define a simple function that generates a sequence of Fibonacci numbers. For this first test, we're going to modify this function to print out our values so we can visualize how complex this computation really is. Of course, printing also takes CPU power, so we'll remove it for our later tests. Next, let's wrap our call to fib so we can call this function from our unit tests. We'll start by creating a new function that takes an int and passes it along to a call to our fibs function. I'll name this function fibwrap and simply call my fib function, passing along my parameter. This is all we need to establish a baseline test. In your test suite, add a placeholder for an instance of your memo class and then initialize it in your setup function. You can set your instance to nil in your teardown function if you choose. Next, we'll add a call to our fibs function and pass in a value of 28 to see some activity in our console window, and we'll run the test. Obviously, this test is flawed due to our print statement requiring CPU power, but this does serve to illustrate how much work is being done to generate 28 levels of Fibonacci numbers. Notice in this continuous stream of numbers how many of them are repeated. This is a strong indication that we're making the same computation over and over again. More on this in a moment. Let's remove that print statement and then rerun our tests. It finishes quite a bit faster since we aren't printing each value as it operates. Let's up the number to 45 for a more substantial set of operations, and we'll run the test. This time, our operation takes well over 10 seconds to complete. This drastic time increase is because the order of complexity of this operation is exponential, or O times 2 to the nth power. We saw in our first test how many repeated computations were occurring. We can introduce a caching mechanism that stores references to these computations to avoid the extra work. Above our fib function, we'll create a new dictionary that will act as our cache. The key will be an int and the value a double. Then, at the top of our fib function, we'll check our fib memo dictionary for a key that matches our input's value. If the key exists, we'll simply return our stored computation result and forego further computations. If the value does not exist in our dictionary, we'll proceed with our computation. Then, below our computation, we'll take the result and store it in our dictionary, using our function's input for the key and the computed output for the value. Then we'll return our result. If we run our test now, we should see a much different result due to our newly installed caching mechanism. And we do. We see that our computation was completed in less than 1/1000th of a second, which is a staggering difference from the non-caching version. And this operation can be done using generics, making our memoize function more useful in general. For brevity, we'll paste in a generic memoize function and break it down line by line. So this is memoize, as it was presented by Apple in session 404. We'll start our deconstruction at the method signature. First, we see that our memoize function accepts a dictionary whose key conforms to the hashable protocol and is represented by the alias t, while the dictionary's value can be of any type and is represented by the alias u. Next, we'll look at our single parameter, which takes a function. The input function itself takes two parameters. The first parameter is yet another function that takes a type t and returns a type u, while the second parameter is of type t. Finally, our input function returns a type of u. Our memoize function itself also returns yet another function that takes a type t as its input and returns a type u as its return type. Next, we see our variable named memo, which is a dictionary that matches our input dictionary. This represents our cache. Then we have a result placeholder, which will contain a closure, which in the next line gets its value. The closure we're assigning to result first checks our cache for the existence of a stored computation. If one exists, we simply return the stored computed output. If one does not exist, we'll perform our computation by calling our passed-in closure and providing it our result along with our key to compute a value. Then we store our computed output in our dictionary and return our value from our closure. Finally, we return our result. Now let's put this memoize function to work. We'll start with a simple wrapper function named memowrap, which takes an int and returns a double. Then we'll define a new constant named Fibonacci, which will also get a type of takes an int and returns a double. We'll set it equal to our generic memoize function, and we'll paste our Fibonacci computation into its closure. Now let's rewire the test and use our memoize function. That should do the trick. Upon running our test, you see that we get similar times to our previous cached version. Before we move on to the next video, I wanted to once again point you to Colin Eberhardt's Game of Life tutorial. As I mentioned at the beginning of this course, Our version of Game of Life was based on Colin's version over at scottlogic.com. If you want to learn how to utilize memoization to drastically improve your Game of Life, follow this link over to Scott Logic and see Colin Eberhardt's excellent demonstration. You can find a direct link on this video's resource page. In this section, we learned how to measure and inspect our application's performance with Time Profiler and XCTest. We saw how whole module optimization gives us a free performance boost and how we can improve those performances by reducing dynamic dispatch and reference counting. We also learned about how the generic specialization optimizer improves the performance of our generics. Finally, we introduced Big O notation and algorithms like memoize. In the next section, we'll look at some common design patterns implemented in Swift. Hello and welcome to Section 8, Design Patterns. In the previous section, we saw how to drastically improve the performance of our applications. In this final section, we'll be discussing design patterns. We'll start by introducing the importance of design patterns. Then we'll look at 2 design patterns from each of the 3 major categories of patterns: creational design patterns, structural design patterns, and behavioral design patterns. Now we'll move on to the first video of this section, which will serve as a design patterns overview. In this video, we'll discuss design patterns and why they are important. We'll also discuss the 3 major types of design patterns. A design pattern offers a general reusable solution for a given common programming problem. As developers, we tend to encounter many similar types of issues over and over again. With that in mind, it makes sense that when design problems arise, that we leverage the solutions cultivated over the years by a global community of developers. So what are some of the reasons to use design patterns? Some may argue that the implementation of a design pattern costs developers time, making design patterns an unsuitable choice while programming. However, when considered over the lifetime of the application, design patterns can prove to save time and money by providing tried and tested solutions that are predictable and clear. Design patterns also offer improved communication between developers. Think about it, it's much easier to talk about singletons than to talk about classes where we are only supposed to have one instance at a time. We're going to discuss design patterns in the scope of 3 different categories: creational, structural, and behavioral. Creational patterns deal with object instantiation mechanisms. Creational patterns address design issues that result from the basic form of object creation by controlling the way that objects are created. Structural patterns are patterns that ease the application's design by identifying elegant ways to architect relationships between entities. And behavioral patterns are built around common communication patterns between objects, which improves the flexibility of communication between objects. Now, we obviously won't be covering every design pattern available in our course. There are so many design patterns out there that one could easily write an entire course just dedicated to design patterns. Having said that, I've chosen 2 common design patterns from each of the 3 categories as an introduction to design patterns. If you'd like to find some useful resources on design patterns, visit this video's resource page. In this video, we've made the case for using design patterns while developing. In the next video, we're going to take a look at the first of our 2 creational patterns, the singleton pattern. In the previous video, we discussed design patterns in general. In this video, we'll be discussing the singleton pattern and we'll see how to implement it in an application. The singleton pattern ensures that only one instance of a given type exists in your application's lifetime. This is achieved by creating a single instance of an object within the singleton and by making the initializer private to prohibit outside instantiation. Any further reference to the singleton object simply refers to the underlying instance. This pattern can be used for modeling finite real-world resources like a server or a printer. For example, perhaps your object manages a connection to a printer. Instantiating a second instance of your object doesn't create a second printer in the real world. So singletons allow you to create a shared instance that allows your single object to be used throughout your application. I should note that there is a lot of controversy about singletons. I've provided some links to some excellent discussions on this video's resource page. But to name a few, singletons can make your application difficult to test. They are often used as a hack to create global instances, usually to avoid the work of passing values properly. For the most part, you should rarely use singletons. In fact, one of the main reasons why I've chosen to include singletons is to warn you to actually resist the urge to use them. You can download the singleton project files on this video's resource page. Once your project has loaded, open up the file named logger. Here we have a simple logger class with some properties, a write function and a read function. The problem is that this class can be instantiated over and over, with each instantiation pointing to the same file. This can be problematic when you consider multiple processes writing to the same log simultaneously, and before one process can finish, another process tries to log using another instance. This is one of the few times when a singleton class is appropriate, since our logger may have limited resources, such as a synchronous database connection or a log file. Now, there are many ways to create a singleton class. However, the one that I'm going to show you is considered the best practice by both Apple and the Swift community. You can visit this video's resource page for references to this. At the top of our class, we'll add a static let named shared instance. This shared instance will hold the one and only instance of our logger class that will be possible in our application. We ensure that this is the case by including the private keyword on our initializer, making it impossible to instantiate multiple instances outside of our logger class. Of course, now our instance of logger in our view controller is broken. If we look at our instance, it says logger cannot be constructed because it has no accessible initializers, which is precisely what we wanted. So, we can update our calls to logger by changing our calls to logger.sharedInstance.write. We can now use this singleton anywhere in our application. There are some complexities, however, when dealing with finite resources and concurrency. For example, what if we try to write to our logger from multiple threads at once? Let's see what happens. In the viewcontroller.swift file, add a function named runBackgroundLogs. We'll call this function just above our for-in loop. I'll paste in a background queue implementation, which should be familiar to you. Notice that our background queue is simply performing the same loop as before. Let's run our application and see what happens. Just as expected, we receive a runtime crash. This is a key example as to why singletons should be used with caution. This is a simple fix, however. We'll head over to our logging class and use Grand Central Dispatch to resolve our problem. So, the problem at hand is that our application is attempting to access our data source concurrently. We need to force our write method to handle requests in serial. We'll add a private constant named queue and give it a value of dispatch_queue_create. I'll add an identifier named log_queue with a type of dispatch_queue_serial, which gives us a serialized queue. Next, we'll wrap the contents of our write operation with a call to dispatch_sync, and we'll give it our queue to work with. This should do it. Build and run, and your application should work flawlessly. In this video, we have looked at the correct way to implement a singleton in Swift 2. In the next video, we're going to take a look at our second creational pattern, the factory pattern. In the previous video, we looked at our first creational pattern, the singleton. In this video, we'll look at the factory pattern both conceptually and in practice. The factory pattern replaces class initializers and abstracts away the process of object instantiation, allowing the type of the object created to be determined at runtime. This pattern consolidates logic that decides which implementation to instantiate into a single function inside of a factory class. The major benefit to this pattern is the abstraction of object logic and controlled management of object creation. We'll begin by opening the starter project for this video, which can be found on this video's resource page. This project is a console application that contains a few simple classes that connect and upload files to different cloud accounts depending on their file types. We've got one account for work-related files, one for personal files, and one for backup files. Of course, when you open one of these files, you'll see that we're not really connecting to a database. We're just printing messages to the console. The inclusion of that kind of development is outside the scope of this demonstration. We're only interested in the factory pattern here. So, in this hypothetical situation, we're tasked with uploading a batch of files to 3 separate cloud accounts. The file type is what determines where our files are uploaded to. Clicking through these classes, we can see immediately that they are very similar. Each has an account number, a password, and 2 methods for uploading and fetching. If we open main, we'll see 3 class instances, a file path variable that holds several strings, each with a different file extension and a loop with some logic. If we run the application, we'll see success messages printing to our console for our file uploads. The problem that we can solve here with the factory pattern is with our explicit instance creation and lack of abstraction around our logic. Right now, we're managing the creation of our objects ourselves. In a more complex situation, with many more account types and file types, this could not only become cumbersome, but it could even lead to potential issues. Not to mention that we have some very similar classes that have no real relation to each other. We'll convert this into a factory pattern, which will allow the type of the file we're uploading to determine the creation of our storage class type. We'll create a new file named Cloud Storage. Then we'll add a protocol with the same name. It will hold an account number, which will be read-only, a password, again read-only, and 2 methods, an upload method, which will take a file path, and a fetch method that is just there for show. Now we'll go through each of our cloud storage classes and make them conform to the cloud storage protocol, which should go pretty smoothly considering that our classes already implement each of the required properties and functions. Now that we have that in place, we'll create our factory class. Add a new file and class to your project and name it Cloud Factory. We'll start by defining an associative enum named file type. This isn't a requirement of the pattern, but it will help to improve readability. Our file type enum will implement Swift's string type and will define our 4 cases. Images, which will hold a string with the PNG file extension. Videos with MOV. Archives with zip, and docs with pages. Of course, this is hardly an exhaustive list, but it serves just fine for this example. Next, we'll move on to our Cloud Factory class definition. We'll add a class function named accountForType. AccountForType will take a string and return an instance of a class that conforms to our protocol, Cloud Storage. I'll paste in the logic that will determine which instance to create. Here, we split our string at the period, and then we get the last item in the sequence and create a string from it. We'll pass that string into our enumeration, and then we'll switch based on the respective enum type. Finally, let's update main to use our factory instead. We'll remove our instance and the logic inside of our for loop. We'll then call our Cloud Factory's accountForType function and pass in our file. Thanks to our protocol, we can call upload since any possible type that will be created here is guaranteed to have an upload method. Finally, we'll pass our file into the upload method. I should note that we could have used initializers to get this file variable into our classes, but the factory pattern purists prefer that no initializer is used. One important thing to notice when looking at our Cloud Factory call is that there is absolutely no awareness of type. Our factory will pick out and generate the proper class instances based on the file that we passed in. We'll run this and, as before, we see all of our files being uploaded to their correct storage accounts. In this video, we have seen how the factory pattern can eliminate the need for explicit object creation. In the next video, we'll look at our first structural pattern, the adapter pattern, which can help us to adapt to incompatible APIs. In the previous video, we looked at the second creational pattern, the factory pattern. In this video, we're going to take a look at the adapter pattern and see it in action. From time to time, we will find ourselves in a position where we need to make 2 incompatible frameworks speak to one another. When we find ourselves in this situation, we'll utilize the adapter pattern. The adapter pattern allows us to integrate components from third-party frameworks or legacy APIs whose source code we don't have access to in our code. Feel free to download the project files for this video at this video's resource page. Let's begin by opening up the starter application. Here we have a fake music player in the form of a console application. If we run our application, we'll see some song objects appear in the console window. If we open our main.swift, we'll see an object named player which has 2 music collections loaded into it. So we're effectively merging 2 music collections into a player object, and then below, we're printing the objects out using a for in loop. Let's open our song.swift file. Here we have a song object that contains 3 properties. Then below we have a protocol that represents our playlist data source. Any class that implements this protocol will have an array of songs, an arrange by name function, and a random function. We can think of these types of classes as a collection of songs. Next, we'll open datasource.swift. At the top, we have our data source, which will act as our base class. Data source implements our playlist data source protocol. So, any future class that inherits from data source will automatically implement the playlist data source protocol. Down below, we've got 2 music collections, one for electronic music and one for rock music, and they both inherit from the data source base class. These classes just populate the inherited songs array with songs from that given genre. Finally, we look at our player class. Here we see a class that contains a property named collection that holds an array of any item as long as it implements playlist data source. We've got an initializer that takes any number of playlist data source objects. We have a playlist variable and a randomized variable. So we have a system here that allows us to add collection after collection of music to our playlist, as long as the collection conforms to playlist data source. But what happens if we're given a collection from a different system? Of course, maybe we have access to the new collection's source code, and we can make the necessary changes for it to adhere to our protocol. But what if we don't have access to the source code? This is where the adapter pattern comes into play. We can create an intermediary adapter class that enables our 2 APIs to work together seamlessly. First, let's add the incompatible music collection. Let's add a new class, and we'll name it Imported Music Collection. We'll add a class named Recording, which I'll paste in now. This class has 3 properties and an initializer. We can see that the file types are all NSString, as opposed to our string file types in our other collections. Next, we'll add another class, which will be named Imported Music Collection. We'll just add them in the same file for brevity. I'll paste in the code for this class. We see that it contains a playlist that is of type dictionary with ints as our key and our recording type as our value, an initializer that populates our playlist, and finally, we've got a getPlaylist function at the bottom. So this code is clearly incompatible with our other music collections. We've got different types, and let's just say for this exercise that we don't have access to the code in these classes. So how do we integrate? The answer is that we build an adapter. Let's add a new file, which we'll name Import Adapter. We're going to add a class named Import Adapter, and I'll add the code for this class. First, notice that we're implementing our playlist data source protocol, making it eligible to be passed into our player class. Then, we've got a private constant that holds our imported music collection, which we initialize in our initializer. To satisfy our protocol, we've got to add our arrange by name and random methods below. The important part is our songs variable. Here's where we're actually adapting our imported playlist of our recordings with our song struct. Notice that we're fetching our record instance's name, album, and artist values and casting them from NSString to string. Now that we've adapted our imported music collection, we can now update our collections in main with our new import adapter collection. We can run our application to see that we've successfully added it to our collection. In this video, we've adapted 2 incompatible APIs using the adapter pattern. In the next video, we'll look at the second structural pattern, the facade pattern. In the previous video, we looked at the adapter pattern. In this video, we'll be looking at the facade pattern. The facade pattern allows us to provide a unified interface to a set of operations in a more complex subsystem. When facade is properly implemented, it offers us a high-level interface that makes the subsystem easier to use. You can think of the facade pattern as a type of adapter pattern, but over a larger span of operations. Let's begin by opening our starter files for this video, which can be found on this video's resource page. This simple console application simulates a portion of an application that manages files. If we click on User Repository, we'll see a struct for a simple user object and a class named User Repository. This class has a function that manages some REST API calls and a switch statement at the bottom. So it's essentially a consolidation of REST logic. We can see that our manager function takes a user, an operation, and a completion handler. We can click on both the file and the article repositories to see that they are nearly identical. We've also got a file name control that contains two simple enums for our status messages and our operation types. If we open main.swift, we can see that we've created some simple objects, and we've made a few calls out to each of our repositories where we're passing in objects and selecting which operations to perform. If we run our application, we can see in our console window that everything runs smoothly. This same set of operations could be achieved in a much cleaner way. However, rather than calling each of our repositories manually, we could just call one class and let it determine where to send our file. Here's where the facade pattern comes in. Let's add a new file to our application and name it Connect Facade. We'll define a generic class named Connect. This Connect class will hold an instance of each of our repositories. Next, we'll define a class function named Handle, which will take our object of type T and our operation that we'd like to perform. I'll go ahead and paste in the logic that determines which class instance we have. All we are doing here is checking to see if our passed object is a user, a file, or an article. If we get a match, we pass our objects and operation type into the proper repository. Now, I should mention that this code is not ideal. For instance, it can only manage 3 types. We're also not dealing with any of the edge cases or the necessary error handling that would go along with operations like this. This example was simply designed to convey how the facade pattern works. Alright, now that we have our Connect class complete, let's update main.swift with some new calls that will perform exactly the same. I'll delete all of our user repository calls, and we'll simply call our Connect class, then Handle, and then we'll pass in our user and our operation. If we build and run our application, we see that we're able to perform the exact same tasks as before, but using our new facade pattern API, which is more readable, cleaner, and less lines of code. In this video, we saw how the facade pattern can result in an elegant API. In the next video, we'll discuss our first behavioral pattern, the chain of responsibility pattern. In the previous video, we looked at the facade pattern. In this video, we're going to apply the chain of responsibility pattern to the repository API we saw in our last video. The chain of responsibility pattern allows for the decoupling of a request sender from the receiver that eventually handles the request. I say eventually because with this pattern, our request is sent down a sequential chain of potential handlers. One of the handlers is hopefully able to accept the request. If no handler can accept the request by the end of the chain, the request is not able to be handled. I should mention that this is a popular design pattern for handling events in the Cocoa framework. Let's see this in action by opening up the starter files for this video, which can be found on this video's resource page. Once you unzip the package, you'll notice that we're using the same starter files from the facade pattern video. Upon loading the application, we see the same files as before. I'll start by renaming my Connect Facade file to enum to avoid confusion. Next, we'll create just one new file named repository. We'll define a class named repository, which will have a property named nextLink, which will act as an optional placeholder for a repository type. We'll add an empty required initializer, which we'll need in a moment. We'll add a function named handle that will take a generic type T and an operation type. In this function, we'll check if our next link is nil. If it is, that means that we have reached the end of our sequence. If it isn't, that means that we have not reached the end of our sequence yet, so we'll pass our object along to the next item in the sequence. Before we finish with our repository class, let's make sure each of our 3 repositories inherit from the repository base class. Now that we have our repositories inheriting from the repository base class, we can complete our repository definition. Next, we'll create a class function named createChain, which will return an optional repository. I'll paste in the code for this function and break it down. Here, we are creating our sequence of repository classes. Then, we will loop over our repository classes in reverse sequence. Starting at the end of the chain, our first existing link will receive no value. Then, we'll initialize our given repo by calling its initializer. Then, we'll assign an existing link to the repo's nextLink property. In the first iteration, this existing link value will be empty, which is why we have reversed through our sequence. All future instances will get a proper next link value. This repository will serve as a base class for our other repos. So let's put this base class to work, starting with our user repository. I'll add an override function for our base class's handle method. I'll paste in the code and break it down. Here, we're checking to see if our generic T object can be cast into a user object. If it can, we will call our user repository manager and pass along our object in operation. If our object can't be cast, we'll call our super handle and pass along our objects to the next item in the chain. Believe it or not, that's all that we have to do for the chain of responsibility. We'll just duplicate this logic in our other two classes, and we'll be ready to call it from main. I'll copy my handle override and paste it into file, and then change my handle function to work with file rather than user. I'll do the exact same thing for the article repository. Once done, open up main.swift. We'll delete everything except for our variables at the top. Then we'll create an if-let and assign it a value of repository.createChain. Then we'll simply call chain handle for each of our objects. Build and run. You'll see that your messages are writing out just the same as they did with the previous example. Let's take this one step further and add an incompatible type. Define a struct at the top of main.swift named vehicle and give it two properties, a make and a model. Then let's create an instance and we'll add it to our if-let statement. This time, when we build and run, we should see that we've reached the end of our chain without our object being handled. In this video, we have seen how to apply the chain of responsibility pattern to our repository API. In the next video, we'll introduce the second behavioral pattern that we're going to look at, the observer pattern. In the previous video, we applied the chain of responsibility pattern to our repository API. In this video, we're going to look at another very common pattern in the Cocoa framework, the observer pattern. The observer pattern is used to allow another object to publish changes to its state, which allows for loosely coupled communication between two objects. This is done by implementing a protocol delegate relationship between two classes. This pattern is not just limited to two-way communication. You can also define a one-to-many dependency between objects. So, as one object changes its state, all of its dependents are notified and updated automatically. Since this is a simpler design pattern, we won't need to do much to get our starter project, which you can find at this video's resource page, up and running. Once you have the starter project open, let's look at viewcontroller.swift. We've got a property observer named enteredNumber, and we've got a numbersEntered IBA action that assigns numbers from the UI text field in our property observer. If we click on our observing view controller, we have a few labels for holding numbers, and that's about it. If we run our application and try to enter some numbers in the text field, we don't see anything special. We do see some numbers in the console, but clearly the desired intention is for our labels to be populated down here. So let's fix that by setting up our simple observer pattern. Open viewcontroller.swift and add a protocol named propertyObserverDelegate and give it a type of class. In this protocol, we've included just one function named didChangePropertyValue, and we'll pass in an int named value. Next, we'll add a weak property to our view controller and give it an uninitialized optional type of propertyObserverDelegate. Then, in enteredNumbersDidSet, we'll pass our enteredNumbers value into our observer's didChangePropertyValue function. That's it for our view controller class. Next, we'll open up our observing view controller class and make it implement our propertyObserverDelegate. In order to implement our protocol, we'll need to add the didChangePropertyValue method. Then, we'll need to add some values for our labels. Finally, we just need to set our delegate in our viewDidLoad. I'll paste in the code for that and explain. So in this first line, we're fetching our appDelegate instance, and then we're finding our root view controller, which we know is the view controller, so we can safely cast it. Finally, we set the delegate in our view controller equal to our observing view controller. That should do it. Let's test our application. As we type into the input field, we can see our labels updating with values. This, of course, is a simple version of the observer pattern, but it's a pattern that you'll use all the time in Swift so make sure that you know it well. In this section, we introduced design patterns, and we learned why they should be important to us as developers. We looked at 2 creational design patterns, 2 structural design patterns, and 2 behavioral design patterns. Congratulations, you've finished mastering Swift 2. In this course, we've looked at functional programming concepts like extensions, generics, higher-order functions, sequences, and generators. We then moved on to memory management, where we learned how to profile our code using instruments. Next, we saw how we can interoperate with other languages like Objective-C, C, and even C++. We looked into concurrency and asynchronous programming, followed by ways in which we can improve performance. Finally, we looked at how design patterns can solve common programming problems. I've introduced you to many topics in this course, but it's up to you to pull the threads and see what unravels in your programming career. The next step for you is to dive into Apple's wide array of documentation and learn more about the Cocoa framework. There's also a wealth of information on Stack Overflow to help you along the way. Though, what I recommend most is that you build your first real application. I promise you, that will be the best learning experience that you can find. If you have any questions, you can always contact me on my blog over at www.codebaloo.com. Or you can always message me on Twitter. My handle is @transfer_point. Thank you.